We Are Developers is my favorite conference. It's the only one I'm going to this year because it's really for developers, it's by developers, all the content is real technical programming content.
Hello everyone and welcome to another episode of our Live Days. My name is Benedict, I'm Community Manager here at WeAreDevelopers and I'm happy that you all made it today. So before we start with machine learning, just a quick reminder that our World Congress is back as an in-person event next summer in Berlin. New this year is, for example, a premium pass who grants you access to the speakers launch. So for further information, go to worldcongress.dev and claim your discount on the early bird tickets. And before we start with the talk, remember we have a Q&A section and the chat. Feel free to interact it. But keep in mind, be nice to each other and respect each other as we have a code of conduct. Here's a short video about it. And right back to machine learning. First speaker of today is machine learning researcher at ZF Friedrichshafen AG. He studied mechatronics and information technology, and now he researches deep learning technologies for automated driving systems. Welcome, Niels.
Hello, everybody.
Hello, Niels. Happy to have you. So, hope you're doing fine, and maybe you want to tell the audience and me a bit about what we are going to learn from you today.
Sure. Today we're going to learn about how ZF uses deep learning technologies to perform a scene prediction or to anticipate future traffic agent behavior in order to be able to develop and deploy automated driving systems and ADAS systems or ADAS driving functions. So,
so
yeah, with that. Sorry.
Okay, sorry. All right. So here we might get a glimpse on the future of automated driving. You got my full attention, and Niels, I would say the stage is all yours.
Okay, so yeah, so let's dive into my presentation. My presentation will consist of 4 parts. First, I want to talk about the motivation of scene prediction and how it fits to the ZF strategy. Then I will talk about the training process and data that every deep learning model, of course, needs, before showing you some models we use and show the results of the models, and also show you how we can use those models to power the AD functions mainly. So that will be the main part here. Okay, let me talk about the motivation first. We at ZF follow the strategy of next generation mobility now. This means that we want to deploy technology or deliver technology which supports all 5 levels of autonomy in automated driving functions. Within this strategy, we have 4 major fields where we can use scene prediction in order to power driving functions. The first one is the most obvious one. It's automated driving. Here, we want to anticipate the behavior of other traffic agents in order to be able to safely navigate through it. Another field is the integrated safety field. Here, we want to reliably trigger emergency functions such as automatic emergency brakes or automated emergency steerings. Further, we can also use scene predictions to comfortably and conveniently control our vehicle. So if we anticipate the behavior of the traffic participants, we can increase comfortability. And also we could increase energy saving in electric mobility because we could better anticipate when to recuperate energy or when to not do. So as you see, scene prediction is a hidden but very important part of almost any ADAS or AD driving function. As these driving functions evolve into more complex scenarios, of course, the requirement to such a system increases. So if we take, for example, a currently deployed adaptive cruise control system, which is basically a system that keeps you at a constant speed, or if you have a lead vehicle at a constant distance to the lead vehicle. Here, the number of interactions we have is very limited. So we actually only have the interaction with the leading vehicle, and also the requirement to the time which we need to predict is very low. We almost do not need a prediction for that leading vehicle because it's easy to anticipate what will happen in the worst case. But as we now evolve into more complex fields, such as the urban area and their multi-lane setup, or even an intersection, these complexities or the number of these interactions and the complexity of those interactions explode. So consider intersection in the urban area. Here you have pedestrians, we have bicyclists, we have vehicle, and all of them interact with each other. And also the interactions might occur quite far future. So here the time we need to predict different agents increases, or the required time to predict these agents increases a lot. And in order to handle this highly nonlinear and very complex environment, we, for ZF, want to explore deep learning methods to master this environment. One project where we explore such algorithms is the KISSAF project. So it's a governmentally funded project where we explore with our partners Inchgreen and Technical University Dortmund how the data needs, the engineering methods, and of course AI algorithms interact with each other, and how we can use this to power next generation ADAS functions. All right, so now let's continue with the training process and the data, because of course every deep learning model needs a training process and it needs data, and the more data the better even. So now how can we formalize the problem of anticipating how the traffic agents or traffic participants will behave in our future? We therefore assume we have a solved perception because there are tons of perception systems which are already deployed in vehicle, and we can use those systems in order to generate object lists and extract dynamic agent data, so actually their history. Further, we also can use map from HD maps, or also it is possible to generate maps from perception. We therefore identified 4 important subsystems to power such a scene prediction. It's a dynamic behavior encoder where we will extract features from the history data of traffic agents, and a static environment encoder which extracts or learns to extract features from the map. Then we use the information fusion layer where we model the interactions, or where interactions between those features are modeled, and we predict the future trajectory of the vehicle in terms of predicting future X and Y coordinates. So that will be the output, or the output of the neural network we use here. We can now use, in order to generate training data, we can now use, for example, the perception system we have. We can perform a 3D object detection somehow and extract these coordinates of the traffic participants. We can overlay the coordinates with map data and use here an intermediate data representation, which is given then input into our net. This net, during the training process, learns to model interactions between different traffic agent participants implicitly from the training data, so in the training process, without an explicit objective, because the objective itself is to minimize the distance between the predicted coordinates and the ground truth. So we want the net to learn to imitate the future behavior of the other traffic agents. And our initial setup is that we take 2 seconds of history in order to predict the next 3 seconds of the future. For such training process, as said, we can use the perception system with collected data, but also different data. So, and mainly there are 3 pillars for our project for data which powers such training process. The first pillar is publicly available data. There are many different open source data sets which host also different virtual challenges on different conferences where everybody can participate and compare their algorithms against each other. 2 examples of such data sets is the Waymo open data set, and for example, for highway scenarios especially, it's the NGSN data set. Further, we can use a simulator in order to explicitly engineer scenarios in order to which do not occur so often in the reality. So here we can now engineer scenarios, and even we can perform extremely dangerous scenarios such as crashes. In reality, we don't see a lot of crashes, but in the simulator, we can simulate that without harming anybody. And the third pillar here is the recorded data. So within the KISSF project, we built up a vehicle with a close to production sensor setup. We use a deployed camera perception system and extract data. So let me show you a little bit in detail how such sensor setup looks like. We have different kind of sensors. We have radar sensors, we have LiDAR sensors and camera sensors, which guarantee a 360-degree perception for our car. And now we can drive around with the car and save the data which comes out in an object list format. So far for our prediction, we only use the source of camera data and radar data. The LiDAR data so far is only used as a reference, so the training process does not require the LiDAR data to keep it closer to production and see how far we can get with that. Then, as I mentioned earlier, we have an intermediate data format. We use here the approach by Gao et al., where we use vectorized data. The advantage of using vectorized data against, for example, rasterized map data is that it has lower requirements with respect to computing resources. And we can also represent all kind of data similarly. So as you can see here, we can use vectors in order to represent the history of a traffic agent. Here we can see that in orange, that's the history. Then in green, you can see the future coordinates of a traffic agent, which again are vectors here in green. And also lane markings can be represented in such vectors, as you can see here, the black vectors. A vector always contains a start point and an end point. And for dynamic data, we have timestamps which are added to the vector. And also we can add semantic data or semantic information, such as whether it is a pedestrian, whether it is a vehicle, or whether it is a bicyclist. And also here in purple, you can see we can add to the map semantic information as if the lane marking is part of an intersection, what is depicted here in purple. So that we are very lean, and we can append a lot of information into this data format and continuously, as perception systems get better, enrich the density of semantic information here. All right, let's now take a look at the models we deployed or we tried or explored within the scope of this project or within the scope of scene prediction. We first recreated baseline where we followed the approach by Gao et al. Gao et al. Divides a scenario into several subnodes. And again, subnodes can be of any type. For example, a subnode can be a lane marking, as you might see here. So this would be one subnode, for example. A subnode can be a crosswalk, and a subnode can be an agent. We now use the vectors per subnode and feed it into a pointnet-like encoder, which generates a feature per subnode of same dimensionality. Here it is important to say that through different max pooling operations, the pointnet encoder is invariant to the number of input samples. So we can give per subnode, we have an indefinite number of vectors which can describe such subnode. And also it is invariant to the order of input, which is quite handy when it comes to map data, because it should not matter to the algorithm at which order we give the vectors into it, because they are stationary. They do not change over time. Further, we use a transformer-like architecture in order to fuse the information from the different subnodes. Here, our model learns with the self-attention mechanism how to update each encoding, which is the output of the encoder, per subgraph by the other encodings. So here, that is how the interactions are modeled. We learn to perform a weighted sum per subnode based on all encodings. And this updated encoding for the target agent, which we want to predict, is then given to the trajectory predictor, and a trajectory is generated. So now let's take a look at some results. Here again, you can see the vector format. Orange again, the history. Green is the ground truth where the agent drove in the data, and black and purple are the lane markings. And as you can see here, there is kind of this is part of an intersection, and this is a merging scenario into another road. And as you see in blue, it's the prediction of our algorithm, and it learns to predict pretty well where the future will evolve into, or where the traffic agent's future will evolve into. Further, as I mentioned, we learned to generate a weighted sum based on the encodings of all subnodes or all parts of the scenario. And now if we take a look at those weights and look which weights are the highest, here you see depicted the 5 elements where the highest weights are learned to generate, or where the network, or as we say, the network gives the most attention to. And as you see, this kind of makes sense, right? Because the network gives a high attention to the history of the traffic agent, and also it gives a high attention to the area where the most important map information is, like the merge in itself, the intersection part itself, and also it is the part where most likely the future will evolve into. Another example I want to show is in color generated lane change scenario. Here again, the format is the same. You can see the attention map here, and this is the rendered color visualization. So the target agent, we have built a camera which follows the target agent and shows you how the rendered view looks like. And as you can see, the algorithm learns to predict the lane keeping behavior pretty well. So as long as it goes straight, the prediction is accurate. But as you see here, in the ground truth already it occurs that the agent will perform a lane change. But our algorithm still goes with the most probable future, which is that the agent will continue with the lane keeping behavior, because that is what in the data was mostly observed. But in this case, it doesn't hold true. And this is because the future is uncertainty and multimodal. And what do I mean with that? Let me show you another example. Now consider a car drives down a road and anticipates a pedestrian and the bicyclist. Now, one possibility that our AI needs to deal with is that the bicyclist could stop, the pedestrian could stop, and we can just go straight, which would be kind of easy. Another possibility, which comes with the same history, would be that the bicyclist will not stop, but he will go more or less straight, but still we would adapt our way a little bit in order to anticipate this behavior. And the third possibility of the future would be that the pedestrian performs a cut-in and we would need to trigger an emergency brake, for example. So the key essence here is that for the same history, we have different possible outcomes in the future. Now, how can we empower our neural net to depict or to be able to model such a multimodal future, right? So far, we use only a regular and multi-layer perceptron as a decoder in order to generate one trajectory per target agent. Now, we extend it with the so-called one-to-many mappings. So the MLP now doesn't generate only one possible trajectory, but it predicts several different trajectories. In this case here, there will be 6 different trajectories. In order also to make sure that the network is able to spread those trajectories differently in the future, so to make sure that it doesn't learn 6 times the same prediction, we utilize a variety loss, where only the best trajectory with respect to the ground truth is used to update the weights or to calculate the loss. Also, we want to somehow assess the possibility of the different predictions against each other. So we extend the net with a probability head, which actually is a classifier that tries to classify which of the future trajectories will be the one most or best fitting the ground truth. All right, let's take now a look again at our lane change scenario here. As you can see now, we have different predictions to the left and the right. So our model learns that there's not only one possibility in the future, which is the lane keeping behavior, but it also predicts that there is the possibility of lane change to the left and lane change to the right. And also, as you can see, when it is evident from the history that a lane change will occur, all modes show kind of a lane change, even show the possibility that the lane change might be over 2 lanes, but all modes show the lane change will occur. Also, still looking at the attention maps again, here at the example of a T intersection, where we can see, okay, the model learns to predict accurately that there is the possibility that we will perform a left turn and a right turn. And still, the model knows which parts of the map are the most important one, even in such multimodal training setup. So it takes a look at the left turn lane markings, and it takes it gives the highest importance to the left turn lane markings, and it gives the highest importance to the right turn lane markings, where the agent again most likely will evolve into in future. Now, being able to power a multimodal future prediction, how can we further boost performance here? One thing which I want to take a look at first would be the encoder. As I said in the beginning, we identified 4 different subsystems, but here we only see 3. And because we use the same encoder for dynamic data and static map data. And with this encoder, we, as I said earlier, have the assumption or the property that it is invariant to the order of input vectors. But for dynamic data, we thought that actually the order of input data is quite important because we can gain some information out of it. Like usually in an extrapolation of a movement, the most recent movement vectors would be the most important one, right? So we therefore needed a paradigm that is able to be invariant to the number of input vectors, but can gain information out of the order of input vectors. And then therefore, long short-term memory encoders are very suiting, and that's what we try to apply here. And now having the information fusion layer with one single self-attention module. So this means that interactions between the agents and the map and the agents itself are considered to be quite similar. We thought that these interactions quite differ. So we wanted to deploy one attention module where we can model the interactions between agents and the map, and then another attention module which models the interaction with between agents and other agents. So this together results in our architecture, which we call the vectorized interaction-based scene prediction, or VibesNet. Also, we are not only interested in looking at qualitative results, but also we want to quantify performance here. And one metric to quantify performance from research is the average displacement error or the final displacement error. Both of these metrics based on the displacement error, which is the L2 distance between the prediction and the ground truth. In terms of a multimodal setup, we want to know how well the best mode can grasp the future. Therefore, we use the minimum of those, like the minimum displacement between the best mode and the ground truth. And the average displacement error builds the average over all timestamps in the future, and the final displacement error just takes a look at the last prediction and the last ground truth. So it kind of measures the performance on the long tail of such algorithm. And as we can see from those metrics, adding this two-stage attention and the LSTM encoder can boost performance on public available data by between 20 to approximately 23%. And on our collected KISF data, the performance even boosts more by 36 up to approximately 46% in those metrics. And as you can see, we can train our network with this generalized intermediate data format on almost any data source. Further, we can also use this algorithm to predict or to generate predictions for every agent within a scenario. And then, for example, in a Carla environment or in a Carla simulator, we can feed back those predictions into the Carla simulator, as you might see here, and depict those predictions in this virtual environment. And now if we have a driving wheel, we can drive around in this virtual environment and see how the algorithm predicts us and how the algorithm predicts other traffic participants when we drive towards them and they kind of model the interaction with us. One thing I want to highlight here as well is if you take a look at the collected data. What I forgot to mention here is that in the collected data so far, we do not use the HD map, but we use the lane marking detections from the camera system. And as you see, there's quite a difference between using HD maps and between using the perception system, because the perception system always will be a little bit more noisy, or in the state of the art, it's a little bit more noisy, as you can see here with some misperception of a lane marking. But still, the algorithm learns to handle such noise and predicts that the agent most likely will follow the lane markings and stay in between if there's no alternative in the scenario. Therefore, I also brought two more examples where you can see that even better. Here we have a misperception where the lane markings more or less are shifting off a little bit over the future, because the ground truth here, you can see the ground truth will follow another way, but the extrapolated lane markings do not match the ground truth here. Still, our algorithm learns that the car will stay in future between those lane markings, even if it is not very correct in this case with the future. Another example is here, where you again can see very noisy detection of the lane markings, but still our algorithm learns we will stay in between lane markings. So one possibility is that we will continue lane keeping, or we will perform a lane change here. Now, how can we utilize such a scene prediction in an autonomous driving function? Generally, in an autonomous driving function, we would expect the scene prediction output to being passed into a trajectory planner, which plans the ego vehicle movement in the future. One possible approach would be to use a sampling-based motion planner. So a sampling-based motion planner, we sample from some action space, we sample trajectories, which could be possible for the ego vehicle in the future. We then order those samples with a cost function, and then we return the best feasible sample with respect to that cost function. And what would the feasible sample here mean? So on the one hand, we have kinematically feasibility, which would make sure that the movement is kind of smooth and we do not get in accelerations where we would be subject to some kind of motion sickness, or we make sure that the selected sample is collision-free with the prediction of other traffic participants. Another more modern approach to use such a scene prediction algorithm is to take this prediction for the ego vehicle and give it into an optimization, and then give it to an optimization algorithm that optimizes this prediction with respect to some cost function which we define. Within this cost function, again, we can make sure that there's a proper distance to other traffic participants by penalizing that, or also we can make sure that the accelerations which we perform are not too high. Now, to make this optimization, we want this optimization problem to be differentiable. So therefore, we can use an open source framework, which is the Theseus framework, where there are implemented methods which make this optimization function differentiable. And further, we can then use a loss function, which, for example, which we can calculate then with respect to that cost function and differentiate through the optimization into our scene prediction and update our scene prediction with this loss function from the planning layer. So to sum up, as you can see, the utilization of vectorized data is fast, lean, and promising. Our self-attention-based interaction identifies data of superior interest pretty well, as you might have seen with the map areas where the focus of the network lies on. Our input order for the dynamic data can add quite some information in order to boost performance here, and scene prediction can be utilized in a more modular setup for an AV, but also in a more integrated setup in AV, we can integrate it into an end-to-end stack or an integrated prediction and planning stack and train it end-to-end. So yeah, with that, I want to show you my reference and thank you. And yeah, I'm ready to answer your questions.
Sorry, was muted for a moment. Hello again, Niels. Thank you so much for the very interesting talk. Before we start with the Q&A, just a quick reminder for those in the audience who are watching us on YouTube, to interact in the chat and submit your questions, you need to go to our live page, which is wearedevelopers.com/live. So make sure to watch it on our streaming platform. All right, Niels. So we got some questions submitted. Are you ready?
I'm ready.
Perfect. First question. What level of autonomy did autonomous cars achieve so far?
So far, certified is up to level 3, as far as I'm. So if you want to buy a car which has driving functions, the highest level of autonomy that you can buy is level 3 so far, which is conditional automated driving, and especially this is the traffic jam assist here.
All right, thank you for that. Next question. How AI deals with uncertain inputs that sensors produce during rain, snow, dirty roads, etc.?
So yeah, generally that's a big problem for for deep learning itself. So I myself assume solve perception, but for perception, it's a big topic. So there are different techniques which try to firstly detect that such uncertain environment occurs, and then we try to adapt it into a domain where we know we are able to handle the data. And if we cannot transform it into that domain, we want to make sure that we fail safe. So we need to have some safety function that says, okay, this is a situation I cannot handle. Now, please, driver, take over for level 1 to 3, because there still needs to be a driver, or maybe in worst case for level 4 or level 5, drive to the site and call supervision.
All right, thank you for that answer as well, Niels. Next question. What can you recommend to get entry-level jobs in machine learning, data science, and so on?
So yeah, first, of course, if you want to acquire those skills, I can only recommend you to try out. Just go on Kaggle, for example. I don't know, there are tons of interesting problems. Take a look at it, try out to develop your algorithms and get used to the different languages and different techniques you will use there. Then I would recommend you to use different blogs there, or also videos, or listen to different talks about it. And then I think what is quite a good entry is to go and start with research and applied research. For example, my entry point was my master thesis. I came from a quite different background. Like, I came from mechatronics. I was not so used to do deep learning, but I wanted to challenge for my master thesis, and I just tried it out and went for it. And yeah, from that point, I was super excited about deep learning. And that's how I would recommend you to do it as well.
All right, thank you, Niels. We get another question. What happens if AI is not able to avoid a car crash? So if I interpret it correctly, do you have legal information, I think?
Yeah, that's actually an unsolved problem, and that's what is the task for legislation for the next year. So we cannot deliver a technology, or that's not a case of technology, right? It's a case of how the legality will look like. And so far, like, there are some guidelines, like the AI Act, which somehow tries to ensure the responsible development of those AI systems, but still it's very uncertain. And that's like the exciting part over the next years for autonomous vehicle or the whole automotive industry, because we are in a transformation process currently. And that's one of the exciting things for future to shape.
As it is often with newest technology. Yeah. We got another question. How does AI interact with physical parameters of an environment? Car size, car weight, engine characteristics, eyes on a surface of a road?
So, of course, we can use all of those data in the training process. So that would be the straightforward way. We enrich our information on which we train the network with those data and try to teach the model to learn the physics behind that. And also, there are more and more techniques evolving into so-called physically informed neural networks, because as you know, neural networks are differentiable. So we can use networks as functions in order to, for example, use solve differential equations as well. So that's where research is currently heading into, because also we increase explainability of a neural network with that. If we know explicitly a neural network follows a physical law, it increases explainability and therefore acceptance in the market.
Okay, thank you for that answer as well. We got another question. What do you think about deep learning AI specializations on Coursera for beginners in AI field?
So yeah, actually, for me, I started with that. So the first course I took a look at was the one from Deep Learning AI, where Andrew NG explains the basics, and I think that's one of the best courses to start your AI deep learning journey with.
All right, perfect. We just got in another question. When do you think cars will drive 100% autonomous?
Yeah, that's a tough one. So yeah, I cannot give you a number on that because I think the technology is quite far in order to, in some areas, deliver it. We have delivered, or there are already at some areas delivered systems. In order to scale it on whole countries, it still will take some time, but I think we will get there maybe in the next 5 to 10 years. But again, we have the problem of legislation and norms to make sure that everything somehow has the necessary feasibility, or we have the necessary tools that ensure some kind of safety and that is backed up by legislation. And that is the more challenging part, I think. And when we solve that, then I think it will be fast that we can deploy those systems.
All right, no specific number, but soon. Follow-up question to the last one. How to implement the infrastructure step by step? Start with highway lanes just for autonomous cars? Last sentence was also a question.
The infrastructure, okay, so, sorry. So yeah, the infrastructure is first, of course, first it starts with data. You need the sensor setup, you need the car, you need to drive around, you need some kind of a storage, and the storage ideally should be accessible from anywhere you want. Then you need your code. So we develop within a Docker container in order to be able to train our systems on almost any hardware. So we can use on-prem hardware, which we have here in ZF, but also we can go on the Azure cloud, which we also use. So we have different systems where we can train our networks. And then, which is the last part, is the ops part. So you need kind of a standard way how you deploy functions into a system. And for us, until now, we are building that in a virtual test drive. So the first step would be a virtual test drive, because here it's easier. You can show the proof of concept and you are safe to not harm anybody. And if you prove the concept, then you will go on a test track and deploy it in an equal manner to vehicle and check it out.
Okay, thanks for that. Talking about your workplace, maybe can you give us some insights on how like a typical workday looks for you, if there is something like typical?
Sure. So we have typical, most of the time I come to work, we discuss with colleagues different new papers which we read, because we have in our AI lab here in Saarbrücken, we have a very wide variety of topics. We have Industry 4.0 topics, we have optimization of lines topics, we have perception topics, and for example, the prediction topics. But the deep learning models which power those topics are or use similar paradigms. So we discuss it a lot about the research. Then, of course, a lot is coding those paradigms with Python and PyTorch mainly, and then training the models on our clusters, and also interact with different collaboration partners. As for example, in the KISSAF project, I collaborate, or I exchange my ideas with the ones from the TU Dortmund or InScreen, and so we have an agile working setup here and are able to go fast on technologies which we want to explore. And also, of course, I can always like bring in my own ideas which I saw from any paper I read, and just try it out.
Sounds very interesting, Niels, indeed. Before you talked a bit about Coursera course you started with. Do you have maybe some more resources like blogs, videos, books, something like that you want to share with the audience?
Yes, so of course, I read a lot in Medium, where there are a lot of articles which also take a look at application of deep learning. If you're more into application, I would recommend to take a look there. There's like tons of articles. Another thing, if you want to learn about the theory, is the book Deep Learning by Goodfellow et al. I think it is publicly available in the internet, and there's almost like any theoretical foundation you would need to to learn how the deep learning algorithms work. So I can recommend that as well. So yeah, that's basically the main sources if you want to continue. And of course, if you want to go really special into application, I did not do it myself, but I've heard only good things about Udacity courses where you can learn on tasks itself.
All right, thank you for this as well, Niels, and thanks for the awesome talk. Thanks for the Q&A. Hope you have a nice day and see you soon. Bye.
Thanks for having me, and I wish you a good day as well. Bye-bye.
Thank you. All right, and because the question came up, these sessions are all recorded and will be on demand in a few hours after the session ended. So, and before we jump to the second speaker of today, we'll have a short break of about 15 minutes. You can use the time to maybe go to worldcongress.dev to get further information on the early bird tickets. See you soon.
People should go to WeAreDevelopers because there are a ton of talks in a lot of different areas. You know, if you program, if you're part of the world of programming, this is the place to go.
think this is a very good and diverse event. And then you also have a chance to talk to different companies and different people to get to know the industry.
To reach so many people face to face in one place is quite unique.
People should go to WeAreDevelopers because there are a ton of talks in a lot of different areas. You know, if you program, if you're part of the world of programming, this is the place to go.
I think this is a very good and diverse event. And then you also have a chance to talk to different companies and different people to get to know the industry.
People should go to WeAreDevelopers because there are a ton of talks in a lot of different areas. You know, if you program, if you're part of the world of programming, this is the place to go.
And welcome back, everybody. Right back to machine learning. Next speaker of today is senior software engineer at Microsoft. He loves to explore all things software and afterwards talking about his learnings. Welcome, Mihailo.
Thank you very much. Can you hear me okay, see me okay, and everything?
Yes, I can see you, I can hear you, everything is in order. Mihailo, thank you so much for joining. Awesome. How are you doing?
I'm actually doing great, to be honest. Just got back from Munich yesterday, and basically I'm happy to be back home. You know?
Home sweet home, happy to hear that. So, Mihailo, regarding your topic, maybe you want to share with us what we are going to learn from you today?
Oh, so basically we are going to talk about decision-making intelligence, you know, and one of the approaches being called the recommendation engines. And that's something that I think we all live with, but we don't pay much attention to. And I think it's time to start paying the attention. So pay attention, I would say.
We will. Mihailo, stage is all yours.
Thank you very much. All right, folks. So let me just switch to PowerPoint. All right. So first things first, and this might come as a surprise to you, but I just recently checked, like literally this morning, And believe it or not, there are 160 cognitive biases identified in humans. All right, that's like 160. That's like 160 mistakes that your brain is making whenever it's trying to make a judgment or a decision or whatever. All right. So basically, if you're thinking that your decision making is rational or it makes sense, well, there are 160 reasons that tell you it's not. All right. And there apparently are the engines that are made to leverage that. And I'm actually happy to share some words about them. Now, before I jump into them, I'll focus on some biases that I think make most sense if you're making recommendation engines, but I'll be also happy to talk about this because I think it highly connects to decision-making process in humans in general. Now, before jumping into like what recommendation engines are, how they work, and stuff like that, I'd like to give you a brief intro of myself, and not because I think you specifically care about who I am, because I'm pretty sure that you don't. But the reason why I want to give you the intro is because I really think it connects really nicely to the whole story. All right, like everything that's about to follow is kind of neatly connected to my background. Right. So you already heard I'm a senior engineer at Microsoft, and my day-to-day work has nothing to do with recommendation engines. All right. I would love to see your faces now, but I could just imagine like, surprise. Oh, so what is he doing here today? Well, hear me out. All right. But there is a but. There is more to the story. So my day-to-day work is basically I'm working as a part of Azure SQL team. I'm working on databases and nothing involving recommendation engines. Ooh, boo, ha, ooh. But he has some things to say. All right. Aside from that, I actually also still happen to spend 7 years in rational emotional behavior called REPT therapy. All right. Like I attended for quite a while. And not just that, I recently, like 9 months ago, became a father to this messenger of Satan himself. All right. Now, what do these three, apparently random facts, like being a senior engineer who's not involved in recommendation engines, going to a therapy for 7 years, probably this guy is a loco, like not that job, not really, I hope, and basically being a father to a kid, right? Well, the last one probably makes you go a bit crazy, right? Well, the thing is, there is a connection, but and this just showcases you why I'm not really a fan of deep learning. All right. So in deep learning, you can actually find some connections that actually do exist in your data, but on the surface area, they just make no sense, right? So what I'm telling you from the surface area, these three completely random facts, they make absolute no connection to each other, right? And yet there is a connection, all right? So being a senior engineer, actually, I worked on a lot of things. Like I've been in software industry for 15 plus years, officially, unofficially for my whole life. All right. I've seen things, I've done things, and basically burned out. All right. So being a senior engineer is what actually got me into the therapy. Going into the therapy, actually, it made me realize a lot of things. But some of the main things I realized is that I basically have, I still suffer from low self-esteem, low self-confidence, and basically my decision-making intelligence is like at the dumbest level. All right. Like there were days when I couldn't decide like whether to go with a black shirt or white shirt, like it was like decisions were just driving me nuts, like, do I do this? Do I do that? What are the consequences? Like, what if I choose this path? Will I suffer? Whatever, like decision making was painful to me. All right. And I'm coming here today to talk about decisions to you. Well, one of the products of, or the outcomes of attending the therapy is that I learned a lot. I got quite interested in humans and how humans think, how do they make decisions. That's how I found out that we have like 160 cognitive biases. All right. I thought it's more like 100, but it's like 160, almost 200. All right. And I learned some things around the block on how do you actually influence people to make decisions, which is basically what you want to achieve with recommendation engines, right? And finally, what does my little son has to do with it? Well, a lot, aside from not letting me sleep. So basically, what's really beautiful, if you have kids, you must have seen it. Decision making or decision making intelligence in babies is one of the most beautiful and one of the purest things that you can ever see in the world. All right, it's like there are no ifs, there are no anxieties. It's literally a straightforward process out of the box. Like, I want that, so I will reach for that. All right, and I just think it's just beautiful that out of the box, nature made us be a great decision making machines. If we want it, we'll take it. All right, and even like I could observe my son in the middle of grabbing for something, he would actually figure out something else, and he would reach for the other thing. All right, so basically you see that out of the box we're pretty good at decision making, and we're probably way more rational than we are as we grow up. But as we grow up, all right, we start being influenced by others. All right, like there is a huge influence of what others like. Well, you are who you are with. All right, and stuff like that. All right, so and then we grow anxious, we grow insecurities, we grow and learn all these things that actually kind of blur our decision making process. All right, now why am I telling you all of this? Well, because if you are building recommendation engines, you probably should know your audience. If your audience is the people, you should probably know some things about the people. All right, now to focus a bit more on the technical side. Another reason why I think it's useful to talk about recommendation engines, and honestly speaking, I don't see much of the talk going on about them. I honestly think that these days recommendation engines are pretty much taking over the world. Honestly, and I'm not even kidding when I say that. And if you're thinking, well, that's not the case, I'm the one in charge, I'm the one in the control, no, trust me. Which movie you are going to watch? When are you going to wake up? What are you going to eat? What are you going to read? Like, when are you going to exercise? Which exercise are you going to do? Everything, and pretty much everything is being gently suggested to you. Like, based on your data and based on whatever, you should probably do this. All right. So almost all of the decision making these days is being taken away from us, honestly. And on one hand, that could be a good thing, because if we offload like which shirts to take, or if we offload unnecessary things to AI and to make the decisions instead of us, and assuming that the AI has good intentions, we're good to go. All right. The problem is that the most engines that are being built and that you're probably going to build yourself are actually not inclined to follow the user's preferences, but more like the business preferences. All right. So most of the recommendation engines being built are actually built to influence you to make a purchase or whatever, make some decision that would influence the business. All right. Well, like 99.99999% of them are made with that purpose. And I pretty much tell you that they are taking over the world, and that's why you should know about them. All right. I hope that makes sense. Now, what I usually do before any presentation, I usually go and check like what are the trends and what's going on and what's popular and whatever. So I did that for recommendation engines. Like I checked a lot. I checked a lot because it's one huge area of my interest. I checked what's popular these days, and believe it or not, maybe you know it, maybe you don't know it, but these days it's all about deep learning. All right, like literally everything is deep learning. Deep learning this, deep learning that, blah 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 blah. All right, and that's cool because obviously it does work, right? It's influencing us. We are making decisions. How good the decisions are, that's probably something to be discussed. But obviously it works. It's making us, it's pushing us forward. So I guess that works. But in order to really try and start understanding what's actually going on behind those, like deep neural nets, deep hidden layers, whatever, you actually have to probably understand some ground up work, some basics, all right? Because these basics are actually what is being leveraged by deep learning, all right? So I'd like to open up with basics first, and then we'll slowly build up the story. So I was rehearsing this presentation a lot because I was giving it at a couple of events. live events. So I was rehearsing, in my living room and whatever. And basically, at one point, my wife got frustrated or whatever, and she was like, "Okay, so can you actually explain to me in a simple sentence what the hell recommendation engines are?" All right, like that's. I mean, she was interested, but she was also frustrated, And I thought for a second, and I basically just spit out literally, well, recommendation engines are all about fulfilling the sparse matrices, all right? And I mean, to you, this might mean something, all right? So recommendation engines are all about how do you fill up and rank the sparse matrices, all right? But to her, she's a lawyer by profession. Basically, to her, she gave me that Hindu cow look, like, all right, yeah, whatever. So she just went on with her business, not her area of interest, right? So on a serious note, I mean, recommendation engines really, at its basics, are all about how do you go from unfully or sparse matrix, the matrix with missing values, how do you go from that to a fully specified matrix, all right? And basically, after that, how do you rank the results? All right. So you want to fulfill the matrix and then sort the results and give top 10 ratings back to top 10 rankings, whatever, back to user. All right. So if you're wondering why are they about sparse matrices, well, basically, if you think, I mean, just take Netflix as a basic example, and if you observe, if you take users to be your rows, samples, observations, whatever, and if you take movies to be, the features, dimensions, or whatever, something that you are recommending, basically, I mean, what are the chances that a single user has rated everything, right? I mean, there's just no way in hell that happens, right? So most of the time you're dealing with highly sparse matrices because every user will maybe rate like, I don't know, 1 to 10% of your data, all right? So you really have to figure out ways to actually go from this to something specific. Like once you can predict whether the user would like something, then you take those predictions, you sort them if you have values, right? You sort them and you give to user something that he might prefer, right? Now, you might think there was a whole lot of research and time spent into this. But prior to 2006, that's 2006, they call it like a dark ages of recommendation engines, right? And they call it the dark ages because there was almost nil, like zero research going on into recommendation engines, all right? So why is that? Well, it seems to, I mean, I wasn't dealing with it at the time, but most of the people were interested in data classification, regression, whatever, all those stuff with the fully specified matrices, all right? In data classification, you really have like pretty much defined features, and you have like independent variable that you're trying to guess. Sorry, and there are like a bunch of algorithms that like solve that problem for you, right? When it comes to recommendation engines, well, it's a different story, and probably nobody cares, except, and this is really interesting, except one company who actually bootstrapped the whole effort. And I'll make a small break, and I'd like to ask you to write to chat, what do you think, who actually bootstrapped, who skyrocketed the future research in recommendation engines in 2006? So I'll give it like, I don't know, 15 seconds. So write your guess, your best guess, all right? I don't see anything in chat. If you're too anxious to write. No, sorry, maybe I was looking at the wrong window. No. Okay, I don't see anything in the chat. I'm not sure. Okay. Either I'm looking at the wrong chat or there's nobody watching. I don't know. I don't really know if there is anybody watching.
Hello. Sorry for interrupting. We have a different chat than the others, but I can read some of the answers to you.
No, that would be perfect. Okay.
Amazon, Google, Netflix, Sky, Facebook, Netflix, Blockbuster.
Wow, right.
So just to name some.
Almost there. Almost there. So whoever said Netflix, they were actually right. so not others. It was Netflix. And I'll go back to, give me one sec. I'll go back to presentation. So whoever thought it was Netflix, yes, it was Netflix. Give me just one sec. So, all right. So yeah, it was Netflix actually. So back in 2006, but by the way, thanks for making guesses. I'm sorry that I can't apparently see the chat. But I appreciate the effort. So it was actually Netflix, and back in 2006, that was like 16 years ago, believe it or not, they announced a prize of 1 million. That was quite a lot, way more than it is today, right? They announced a prize of $1 million for anybody who can actually beat their recommendation engine, right? Now, you'd think that competition lasted, well, I don't know, lasted weeks, months, whatever. It actually took 2 years. It took 2 years, and only in 2008, the winning solution was announced. And the winning solution was basically using something that was considered state of the art at a time called Matrix Factorization, which is something that we will talk about a bit later on. And it was using a technique, well, a variation of a technique called singular value decomposition. All right, no deep neural nets, not whatever, and they beat the Netflix engine by 10%, I think. All right, and this is really important moment because this is literally what kickstarted the interest, the research, and bunch of things in the area of recommendation engines. All right, so love it or hate it, whatever. They were the ones who actually influenced this apologies, this area a lot. All right, now. These days, what happened rather recently, and it's not ChatGPT, honestly. So what happened back in September is that one of the biggest recommendation engines, well, one of the biggest influencers in area of recommendation engines, and that's basically TikTok. They announced. They actually published a white paper that describes how their recommendation engine works. And I think it's cool because you can literally see, it's called Monolith, I believe. And I mean, if you would probably guess, and if you guess that it's using like a bunch of combinations of deep neural nets, you would be right. Like it's a lot of deep learning, but a lot, if you go through it and if you dig deep enough, you will actually see that it uses some basics that I'm going to show to you. All right. So yeah, it's all about deep learning these days. You can search for TikTok's research paper, TikTok's white paper. You can search for YouTube's white paper on recommendation engines, whatever. But trust me, the basics is what's interesting. Now, one thing that I really want you to understand about recommendation engines in general, and this is something that's really peculiar about engineers specifically. Like so many times we actually forget that we are actually building stuff for humans. All right, like if you're building a recommendation engine, you're building a recommendation engine for humans. All right, and the problem is that we actually forget that, and we forget that because a lot of us actually like playing. All right, that's why we became engineers in the first place. We like building things, we like breaking things to see how they work, and like we really hate closing things usually. So we usually spend so much time actually, like improving the model, tweaking, like improving this, improving that, whatever. But what we are really forgetting is that the basic premise of recommendation engines is to actually be made for humans and to influence humans to make decisions that would probably make a sale for a business, right? Now, one really interesting thing, if you read any deep enough book about recommendation engines, is that one of the characteristics of recommendation engines is the novelty, right? The surprise effect, And at its core, honestly speaking, at its core, all that people want from your engine usually is to be surprised, right? If you can get this, wow, like if you can get this surprise effect from your user, they would think you made some black magic. All right. And if you remember, I mentioned cognitive biases. One of the really interesting cognitive biases, which I think really kind of fits nicely into the whole story, is this I don't really know the name, but it's basically about the fact that we only remember the peaks of experience. All right, like if you think what you remember from 10 years ago, those would be like some highly emotional situations or whatever. So the thing is, like whenever you're building a presentation or whatever, you have to have some peaks that people would remember, and they just forget everything else. All right. So why is that important to recommendation engines? Well, if we talk about recommendation engines, assuming that you're not working in a, like, I don't know, that you're not recommending drugs or anything that can actually negatively influence people, if you provide some crappy recommendations, I think that's okay. All right. Because if you just keep recommending crappy ones, but occasionally you hit the proper one, well, basically the people will love your engine. All right. And why I'm saying that, well, if you again go deep into Stack Overflow, all right, like there's the trend of going deep into the Stack Overflow, you'll actually see that a lot of people are not sure why we spend so much time building all the crazy stuff when we can actually just take a random item and keep recommending random items, assuming that users didn't interact with them. Just keep recommending random ones, and like 1 in 10 would actually surprise the user, and they will think your engine is the best out there, right? So probably the easiest recommendation engine, like the recommendation engine type 0 that you can build, is just return random items, right? I guess that pisses you, but it actually works, all right? And it works because humans are fallible, as I told you before. Now, there's more, obviously. There are more interesting ones, all right? Now, one funny problem that exists in recommendation engines is, well, how do you deal with a user who just came to your website, your service, or whatever, and basically has nothing rated, all right? So you're not going from sparse matrix to a fully specified one. You want to go from nothing to something, all right? And to my knowledge, there is no mathematical solution like there is for a sparse. You can go from sparse to fully specified, but there is no mathematical approach to go from nothing to something, right? Maybe there is something in quantum, but that's a different story, I guess, right? So let's assume that we have a user, Anna. She just registered to our, the most popular type of recommendation, the movie watching service, and we want to recommend something to Anna, right? Now, this problem of going from nothing, like if you can go from nothing to something, to sparse, well, you already solved part of the problem, right? Because once you have a sparse, like once you go from nothing to sparse, you actually then can apply the years of research to go from sparse to fully specified, all right? So this problem of going from nothing to something has a name, and it's interesting to remember the name because you might want to look into the solutions and ways to actually overcome this. It's called the cold start, all right? And the question is pretty much, how do you go from obviously cold, like a cold cache, like how do you go from nothing to something warm, all right, sparse? Now, obviously, you can look for the latest research and whatever, and I don't know, like there is always a way to overcomplicate it and over-engineer things, and that's absolutely fine. But there are really simple solutions. Obviously, the one simple solution would be just return random items, all right? But there is a bit better way, a bit more sophisticated way, and that's basically just go and ask users what they prefer, all right? Now, If that frustrates you, I'm sorry, but if you really look into how most of the services work, like Reddit, Quora, I don't know, like pretty much any, like Netflix, all right, pretty much any service that you're dealing with will initially ask you, what do you prefer? And then based on that, actually start making the recommendations, all right? Now, this type of recommendation engines, so basically we covered type 0, which is just return random items, but that's not interesting for us engineers. So this type of engines has a name, and that name is content-based filtering recommendation engines. All right. So why are they called content-based? Well, they're called content-based because the whole premise of these engines is to make recommendations based on the attributes of the content. All right. They completely exclude any user's preferences, and they focus only on the content. All right. And if you're thinking like, but why would I exclude the user's preferences? Well, one reason is that you don't have them. Like when you have a new user, well, you don't really know the preference, right? You can leverage stuff like like the geographical area they're from, and then I don't know, whatever. Like people from your area are watching this. You can leverage those things, yes, but it's usually easiest to just ask people what they prefer, and based on what they prefer, actually build some initial recommendations, and then use the feedback loop like to actually fill out the rest of the matrix, right? So in terms of in mathematical terms, like this is a very purely made matrix, all right, but it's made to show to prove the point, not to be mathematically correct. In the case of content-based filtering, there is no user, all right? So our samples, our rows are basically the items that we eventually want to recommend. And our features are actually the attributes of those movies or whatever your item is, all right? So in case of movies, it could be, I don't know, the movie length, the characters, the tags, I don't know, who is the director, whatever. The more features you can get, or the more features you can engineer, the better, I guess, right? Now, but that's something to play with, all right? So the main premise of content-based engines is basically ask user what they like, and based on their likes, which are movies in this case, find the similar ones, and then just recommend them to users, right? It's really that simple, yes. And you can apply deep learning, content-based filtering to that, and you would get the state-of-the-art current research, whatever, voila. All right. Now, one huge problem with this approach is that, well, if you want official definition, it's that human-generated data is temporal by nature. All right. Now, what that really means is that in free form, that usually means that people have absolutely no idea what they want, all right? And their opinions like could change literally in a second, all right? Like you might be a fan of Tarantino for like, I don't know, your whole life, like you watch everything by him, and then he produces a movie that frustrates you, and all of a sudden you start hating Tarantino, all right? And if I keep recommending Tarantino to you, even after you started hating him, well, basically you are likely to start hating my engine as well and leave my service, and basically my business won't be generating any money, right? So the temporality, or basically the changing nature of human-generated data, if you want to go more official, can be solved by a third category of recommendation engines, and that's basically called collaboration filtering based recommendation engines, right? Now, what the hell is collaboration filtering? Well, basically the collaboration filtering, it doesn't officially say that, but it generally abuses the fact, or one of the cognitive biases or whatever, and that's the fact that you are who you hang out with, all right? You are quite likely to have shared preferences with the group of people that you are hanging out with, all right? And that's something that happens, that doesn't, if you remember my baby example, my baby, like my personal baby, like my son's example from the beginning, he's not influenced by what I want. He's absolutely determined, like to do whatever exactly he wants. But for me, if my group of friends wants to watch something that I'm not into, well, there is a high chance that I would do it and probably love it because my friends loved it. Depending on how much dependent you are to their opinion, so to speak, right? So the collaborative filtering basically builds on this fact, and the whole premise of collaborative filtering is really, really simple, right? So let's say we have Darko, and Darko is quite new, so he has a sparse matrix, but he only rated a couple of movies. And if we want to recommend something to Darko, well, what we have to do is basically find users that are similar to Darko, all right? And this is a very small matrix here, but you can notice that Darko and Maria actually liked the first movie, all right? And basically, once we find the similarities, so the chances are if Darko is similar to Maria, all right, then the chances are that Darko might like something that Maria also liked. All right, so Darko might also like the third movie, and Darko will possibly dislike the fourth movie. All right, so the more samples that you can find, the more similarities that you can find, the more confident you can be that that person might actually like like your recommendations. All right. So again, there are multiple variants like user-based if you're focusing on users, item-based collaborative filtering if you're focusing on items. You can do the deep version, deep learning version of it. All right. Well, like there's apparently the deep learning version of everything. But the point is, at the nutshell, it really boils down to you are who you hang with. So just find the similar people and try recommending what they liked. All right. Now, those were the three types. So basically, we covered the random one, which is probably the most memory efficient. We covered the content-based filtering, which was all about, like leverage the content, the items to recommend similar items. And then we talked about collaborative filtering. And if you remember in the beginning, when I was talking about Netflix and their recommendation engines, I told you that the winning solution used a variant of Matrix Factorization, right? So the fourth group that I'd like to focus is Matrix Factorization. Honestly speaking, like the roots of so first of all, it was considered, and I honestly think it still is, the state of the art. The only problem is it doesn't have deep learning in prefix, but I'm sure that there is a deep learning version of it. So the whole premise of matrix factorization actually boils down from mathematics and from linear algebra. And sadly, I'm not a math major, so I can't really go into the proofs and how it works and why it works and whatever. But I turn out to be good at trying to simply explain the concepts. And once I give you a simple explanation, if you want to seek out more details, well, you can obviously do so, right? So I'll give you a simple explanation, but you can just search, for example, for SVD, like singular value decomposition, or SVD++, a bit more efficient version of it. Or there is also like PCA is also considered like a matrix factorization method, like principal component analysis. So the premise of these systems is really simple, all right? And I'll show it to you in a second. So the premise of matrix factorization systems is that you start from a sparse matrix, all right? We have seen this before. And then we actually lower the dimensionality. We do a dimensionality reduction of our matrix, all right? And basically, once we do the dimensionality reduction, we actually end up with a fully specified matrix, all right? And this matrix doesn't have nothing to do with our original data, all right? But I'll get to that. And once you actually, so basically you start from, I don't know, let's say you start from 100 dimensions, you go to, let's say, 10 dimensions. So your 100 dimensions matrix is sparse. You go to 10D, this one is fully specified, and what it contains, I'll discuss shortly. And then you expand that back, you leverage what you found in the lower dimensions, you expand that back and basically use it to fulfill the previously unspecified matrix. All right. So this is pretty much what matrix factorization is all about. Literally going from unspecified to low dimension, and then what you find out in low dimensions applied to actually, to get a fully specified matrix. And once you have a fully specified matrix, well, now it just becomes a ranking problem, right? So the problem becomes, well, just rank what user didn't interact with initially, and basically recommend it, right? Now, how does this work? Well, math, all right? And I'm not a math major. I honestly don't know those things. But there is a method for decomposing matrices in their, like, I'm not sure even how they're called, honestly. But basically decomposing matrices into like some kind of a basic building blocks, all right? If there are math people here, I'm sorry, that's my best explanation. So for humans, like for non-math people, non-math people, the way that the simplest explanation is that basically if you have movies, all right, and by decomposing, or actually let me just go a step back. So one thing that you have to understand about matrix factorization is that it can only work if there is there are some patterns in your data, right? Like if you take a fully 100% randomly generated matrix, assuming that it really is randomly generated, the matrix factorization won't work, all right? So in order for it to work, there have to be some hidden patterns, all right? Now, a good thing about, well, human-generated data is that there usually are patterns, a lot of patterns in what we do and how we interact with stuff, right? So if we are leveraging the human-generated data, there are high chances that it actually has some patterns. We just need to discover it, right? So if you're talking about the movies, well, and if we say that the movies are our columns, features, whatever, the thing is that once you decompose that into lower levels, one simple explanation would be that low levels are kind of the connections, like user A prefers sci-fi horrors, all right, but he hates, I don't know, romantic dramas and stuff like that. Like some combinations of genres, which are actually the patterns, do always exist in data. And basically, like going to a lower level, you're actually observing those internal connections, all right, like the hidden preferences of users in PCA. Those are the eigenvectors, all right, those basic vectors that just stretch, if I recall correctly, all right. So you're observing the basic components, but they don't like they are not your original data. They are some patterns that exist in your original data. And once you identify those patterns, you can actually leverage them back, like basically if I like sci-fi horrors, well, find every movie that appears to be sci-fi horror, and there is a high chance that I would love it, all right? Same would be true for romantic dramas, all right? That's very plastic and simple and whatever, like example of how it works. But it's really that's how it worked, and that's how this system actually built the original Netflix system by 10%, I believe. There is a great paper actually published. You can look it up. I think if you just Google for Netflix, I think Netflix winning solution white paper or something like that, it's actually really written in a user-friendly tone, so you can actually go through it and learn how they built this system. So that constitutes the fourth version, I believe, right? So we discussed random, we discussed content-based, collaborative filtering, we discussed matrix factorization, and basically I come to the dreaded deep learning, all right? Now, as you could probably figure out, I'm generally not a great fan, and I'm not a great fan because, I mean, I guess I just love being in control, and which stems from basically whatever, like a lot of therapy, and I identify that. But I like being in control, and I just generally feel that with deep learning, I actually have no idea what connections are being made, how are they being made, and how is that all influenced. And there is a lot of, like, if you Google for like Google's white paper on typical errors in big data and machine learning systems, you will see that there are a lot of issues with DL because we have no idea what's really happening down there. All right. So deep learning on its own is probably a presentation on its own, but what's actually interesting is that if you look into pretty much, well, from what I saw, actually, if you look into any white paper like YouTube or TikTok or Netflix, you will pretty much see that most of them are just applying DL to the basic concepts that I just described, right? So basically, literally, if you go around and search, you will see that you have a DL for feature extraction, all right? You have a deep collaborative filtering, all right, which is, well, collaborative filtering just with deep neural nets, right? You have deep content filtering. You have embeddings and content mining, all right? Like there are so many things that are actually just building blocks of the basics, just on a higher level, on a lower level, or high level, depends on how you look at it, I guess, and with more computing power, right? So DL is generally great because there is a premise in neural nets that if given a big enough neural net, you can actually represent any function in the world or in the universe, all right? So you're guaranteed that they can actually model pretty much whatever you have. But my problem is that when it comes to recommendation engines, again, I go back to the story with humans. you're working with humans, and sometimes it doesn't have to be over-engineered to actually work. Now, I'll take a second to take a sip of water. I'll let you enjoy this DL for everything slide. Now, the thing is that currently, again, if you look into any practical system, the hybrid systems are the most popular ones, all right? And that's probably, that shouldn't come as a surprise, honestly speaking, because basically people are just leveraging combinations of stuff to actually build more powerful stuff, all right? So it's usually pipes of multiple DL stuff combined together, mixed, and whatever, right? And what I think is quite unfortunate is that there is so much research going into what I just told you about, but there is not that much research. I mean, there are some interesting areas of recommendation engines that I'm going to show you, which don't get much reputation, and I think that's a pity because I think they are really valid areas to explore. All right. So the first one, and my personal favorite, which doesn't seem to be explored well enough, are group recommender systems. All right. So what the hell are group recommender systems? Well, a typical practical problem for a group recommender system would be find me a movie that both my girlfriend and I will like. All right. And I think that it's just an unexplored area because it seems to be an unsolvable problem, like a problem without a solution. But I think we can use some heuristics there. But on a serious side, the group recommender systems explore how do you basically leverage the preferences of a group to build recommendations. All right. So it could be just you and your girlfriend. It could be a group of friends, like which movies to watch based on. So basically, just imagine every person entering their preferences, and then you actually leverage that to find recommendations, right? Those are group recommender systems, and I don't think they're getting much focus, or at least I haven't seen it, but I think it's definitely a valuable area to explore. Then a second interesting area are reciprocal recommender systems. All right. Now the name might sound scary, but it's really simple. Think about dating sites or job search recommendations. All right. So basically, when you're talking about, let's say, I'm just making this up. If you're talking about a normal recommender systems, you know, where you recommend items to user and you hope that user will recommend items, you're pretty much making assumption that item doesn't care who is he interacting with, right? You just care about the user, you don't care about the items, right? Well, in reciprocal recommender systems, both user and item are actually users, all right? Like if you have a dating website, you want to make recommendations to me, you want me to recommend someone that I would like, all right? But you also want to take into account that someone else will also like myself, right? Because if you keep recommending me people that are guaranteed not to like me, well, that recommendation engine sucks, right? I mean, it wouldn't be doing much. And same is for job search. If you keep recommending jobs to me which are not going to take my CV into account, it's pointless, right? And I will stop using your engine. And seems like LinkedIn is on a good path to try to understand that, right? And another problem or another constraint in reciprocal systems is that once you sometimes when you actually do make a match, all right, maybe you have to remove the items from your system, right? If you connect two people, all right, for example on Tinder, chances are that you might want to stop recommending new people to them, all right, because they are out of the system now. Same is true for jobs or whatever. Like so many issues to be solved and so many interesting problems to tackle with reciprocal systems. And finally, the ones that I'm sure you've seen them, maybe you just didn't know that's what they are knowledge-based recommendation systems, right? So knowledge-based recommendation systems are pretty much like the expert search systems where you specify exactly what you want, and it's all about leveraging, like combining that into something practical that you can actually use and leverage it to find the proper recommendations and rank the items and whatever. And a typical problem would be a typical scenario would be like I don't know, the real estate search site or a car search, where you specify exactly what you want. You give me your preferences, and basically I apply that to actually retrieve the information. So it's more like, I'm sorry, it's more in the area of information retrieval than recommendation engines. But at the end of the day, since you have to actually rank it based on the preferences of you really don't want to return the results randomly. You actually want to return them ranked based on what user is most likely to interact with. They kind of are in the rec engine area. All right, and basically that's about it of the rec engines that I have that I can tell you about. I hope I inspired you to look into some of them. If you are more into trying it immediately without trying to understand it, well, there is a great Python library. I haven't used it honestly, but I hear it's great. It's called Surprise. It supports a lot of stuff that I mentioned here, and it's quite opinionated. So basically, it advertises that you can really simply build rec engines in it. So if you want to try it out immediately after this, well, go check Surprise and let me know, did it make any surprises to you, right? In the area of how I like finishing the presentations is I usually like to close up with recommendations on some learning resource, right? So when it comes to rec engines, I mean, there's surprisingly a lot of books, and unsurprisingly, a lot of them are crap, like pure crap, honestly speaking. So 2 books that I would absolutely recommend are Recommender Systems, the textbook, and Thinking Fast and Slow, all right? So the first one was recommended to me, I don't know, when I was in my master's studies by my professor, and it turns out that to this date, I think this is one of the most comprehensive references for recommendation engines. All right, like it goes deep into the math and everything, and you really need to spend a lot of time in it if you want to understand it. But it covers absolutely everything from simple content-based stuff all the way to expert system and knowledge-based and group recommender system, right? So it covers a huge spectrum of stuff, all right? And it's absolute, but it doesn't, at the time when the book was published, I think that probably the deep learning was, apologies, the deep learning wasn't probably that popular. But again, I mean, like if you understand the basics, applying them through a lot of neural nets shouldn't be a huge problem. And Thinking Fast and Slow, if you read this book or if you heard about this book, you might be wondering, why am I recommending this book to about recommendation engines? This book is about people, all right? And not only this book is about people, this is one of the most comprehensive books on people and decision making, emotions, and how irrational we are in making decisions, all right? So I read it once, and I started reading it the second time as well. It really takes a lot of time because it, just like the book on the left, it goes deep into like human mind. Why are we fallible? A lot of experiments that prove how fallible we are when making decisions, whatever. So if you really want to understand how to truly make recommendation engines on a scale built for humans, well, you probably need to understand your audience better. And what a better way than this awesome book, right? Highly suggested. And finally, I was surprised when I found it the first time a couple of years ago, but believe it or not, there is a whole conference dedicated to recommendation engines. Like it's called, it's ACM's Rexis conference. It's held every year. And just imagine a whole conference about recommendation engines, all right? So there is a lot of stuff going on. And what's cool about it is that they have a YouTube channel where you can see the live recordings from every year's sessions. So if you fancy, learning more about recommendation engines, well, this is probably a good station to pay your visit to, all right? So that's actually pretty much what I had prepped up for today. And with that, I'd like to thank you very much. It was a huge pleasure, even though I can't see you. I imagine that some of you might have enjoyed, some of you might have learned something new. Basically, you can find me on LinkedIn. I'm quite active there. Feel free to connect, write, whatever, discuss. I run 2 blogs One is more like a regular blog where I write about everything from machine learning through mental health. It's connected to parenting, that connection. And the second one is a more specialized kind of engineering blog, So check them out if you fancy. And that's about it. Thank you very much. And I'll be happy to answer any questions that you might be having.
Mihailo, hello again.
Hi.
So first, congrats, of course, on becoming a father. And second, congrats on the awesome talk. Because you've wondered, we got some comments. So the audience also loved your talk. One, for example, said, finally someone said it. Deep neural networks are not always the best solution to go with, despite that. So you
glad to hear that.
Got a fan. All right. Mihailo, we got some questions submitted.
Okay.
And if you're ready, let's jump into a short Q&A.
Sure.
The first question would be, what is most used in real case scenarios? Content-based or collaborative-based recommended systems?
That's basically what I try to make a point of. But if you really look, if you look into what popular website, and I generally, honestly speaking, just like I'm not a huge fan of DL, I'm not a huge fan of anybody flaunting with ML when they're really just processing exercised 100 rows or whatever. So if you really look what big systems are doing, all right, and by big systems, I definitely Google is one of the biggest, and Google publishes a lot of papers on ML and all the issues they are having with ML and whatever. So if you look into, Google, Netflix, TikTok, and whatever, you will see that all of them are using combinations of stuff. So it's not a single thing. They're just leveraging combinations of content-based to kind of overcome the cold start, then combo of collaborative filtering and some user modeling and whatever to give you recommendations. And the most basic or the simplest example that you can think about is basically if you go to Netflix, you can literally see all kinds of engines there. You have basic content based, since you liked, I don't know, Terminator 1, you're probably going to like this. Then you have the collaborative filtering. People in your area are watching this, whatever. Then you have some picks just for you, which is basically, then we're going probably into Matrix Factorization and stuff like that. So I would say that from what I've seen, so what data tells me is that it's just combinations that are mostly used in practice, which makes sense if you think about it. I hope that satisfies the question.
I'm sure it does. Thanks for the answer. We got another question. Are the implementation of the recommender systems greater than the amount of attention in research papers actually?
So, can you please repeat it? Is the amount of...
If the implementation of recommender systems greater is then it gets attention in research papers. I think he means that there aren't a lot of research papers about it, and if in a real world scenario there is a higher implementation of these recommender systems, if I'm interpreting it correctly.
Well, right. I see. Well, I can only speculate, honestly speaking. But so from my general experience, it's usually, you usually see this a lot, and it's especially popular now in ML. But we've seen it. If you've been in software long enough, you've seen these trends come and go a lot. So there is a lot. So yeah, there is a lot of research stuff that goes on. So many people jump on that train. So many people have actually no idea how to use that, and they just flaunt about it, maybe talk a bit about it, and then it absolutely does nothing. So I absolutely think that, yes, you're right. I think that we should probably be spending way more attention on basics that we can actually understand and tweak rather than trying to pursue the research, because lots of research just generates a fuss, but eventually it stays in the research domain because it can't find practical appliance, sadly. Some do, yes, but like lots of research is exactly that research and should probably stay on a research level. So my opinion is that, yes, you're probably right. We are too much chasing the novelties when we should probably stick more to what's proven to work, honestly. Even random, like if you really look on the online, a lot of people are so pissed that like they invested so much time and then they compared it to just randomly suggesting stuff to people. And as I told you, people are fallible, and we are fallible, like 160 biases, So you really need to focus on what you want to solve, not what you're building. All right. And I think the basic solutions are the simplest. I hope that makes sense.
To me, at least. All right, thank you. We got another question. You mentioned that in the end, it's all about humans. However, collaborative filtering techniques, even though it is the standard, do not leverage attention mechanisms for the behavior of the user. What are your thoughts on this matter?
You mean, so collaboration filtering based systems are not leveraging they're not leveraging for the events, or what was it saying? Like the daily inputs
they're not leveraging attention mechanisms for the behavior of the user.
I'm trying to understand what does attention making mechanisms. So I will presume that what that means, attention making, like if we are talking about.
We got another question, so maybe the person could specify the question for you, and we go on to the next question if you're not sure.
Okay.
Yeah. All right.
I'm honestly not sure what that means. Sorry. So I'd love to answer, but I'm not sure what exactly it means.
Yeah. So please, if you could elaborate the question, or you can also reach out to Mihailo on his social medias. So maybe there you can discuss it a bit deeper.
Absolutely. Please do. Yes.
Right. Your next question would be, because you work for Microsoft, what do you think about commercial versus open source technologies?
We generally, so basically what I'm going to express is absolutely, and I think I'm even obliged to say this, but that's really what I mean. If you check any of my social media, you will see that everything that I share is absolutely personal opinion, right? So my personal opinion, well, that's a really interesting question, honestly. So I think, one huge problem of open source, which, you have to see it. It's like, if you really dig deep into it, you will see that most of the open source contributors are struggling. Like they're struggling to pay the bills and whatever. And I think that sucks, but on the other hand, that probably just shows you the cruelty of the world, I would say. At the end of the day, just like a recommendation. I honestly don't know what this has to do with Microsoft, honestly speaking. But I'm sharing absolutely personal opinion here. So I think that it just shows you that just like you're mostly targeting humans with recommendation engines. When it comes to world, I think that eventually world revolves around stuff that make money. That's a very sad reality, honestly speaking. But yeah, that's I guess how the world works. Now, if your question was about Microsoft's opinion on open source versus commercial, you would probably have to ask an official from Microsoft. Honestly, I'm telling you a very personal opinion, and I hope that's what you were asking. If not, I'm happy to clarify.
All right. We ran out of time, so if there are more questions to Mihailo, just reach out to him on his socials. We listed them on the live page under his bio. And to you, Mihailo, thank you so much for the interesting talk. Hope you have a nice rest of the day and see you soon. Bye.
Thank you very much. See ya. Bye.
Thank you. Bye. All right, and before we jump to the third speaker of the day, just a few second break. And right back to machine learning. The next two speakers of the day, yes, they come in double. Both work at NVIDIA, one as a senior deep learning data scientist and the other as a senior solution architect AI. So when it comes to machine learning, they certainly know what they're talking about. Welcome, Miguel and Marian.
Thank you, Benedict.
Hello, you
Thank
two.
you for having us today. Hi.
Hello.
Thank you so much for joining. Hope you're both doing fine.
Thank you.
Fine,
Yes.
thank you.
Perfect. So happy to hear that. So would you two mind telling the audience and me just one or two sentences about what we are going to learn from you two today?
Definitely. So, well, basically, this is something that one day Marianne and I, we both work at NVIDIA, and we were talking, what can we do? Something funny, also illustrative of the work we do. And we decided to try and train a mid-sized language model on our local languages. Marianne is French and Spanish, so we decided to train a pre-trained language model on French and Spanish, and to showcase how to do that. So it started like a conversation, and it actually finishing a very nice showcase of how to do it from the beginning to the end, and that's what we are going to cover today.
Miguel, that sounds very interesting, and I would say without further ado, stages are yours.
Lovely, thank you. So, well, this is us. Marianne and myself were in the same team. She's mainly focused on conversational AI and natural language processing. I'm more focused on classical machine learning recommender system, but also on a side on natural language processing. Well, we support our customers on GPU accelerating their solutions. And the first slide, this one is just a joke, okay? It's a nonsense, because even if most of there is a bonus gift for the one who knows what these equations are, because these do not belong to NLP, but the remaining pictures are actually NLP related, natural language processing related. And what we wanted to showcase is that this is how people feel of these Chat GPT or GPT-3 or whatever models, but the reality is not that difficult and not that challenging to make it work efficiently. And that is what we wanted to show you. What we will do basically is we will explain how to download a dataset, public dataset from internet, how to pre-train a language model, and we will see what's that, how to use that language model to perform other tasks such as, I don't know, question answering, translation, and how to deploy that model into production. We will use a couple of models that we created, Mimi in French and Mimi in Spanish. And we will also explain basic things like, for instance, what is model parallelism, tensor parallelism, pipeline parallelism, data parallelism, why we are seeing an increase on the size of the model, why these models are getting better, bigger and bigger. So all those things will be commented hopefully in 45 minutes, and we hope you enjoy it. Okay. So natural language processing basically is a discipline that tries to deal with natural text in order to perform multiple types of tasks, such as, I don't know, creating summaries from a paragraph, or maybe translating, answering questions, sentiment analysis, and many other tasks. So we will try to teach you or to show how to create the core of a language model and use it to perform any of these tasks and many others. Okay, this is what we'll see today. But before that, let's have some perspective. Okay, I think this is since AlexNet, where we have models of around a few 100 million parameters, to last year where we were started talking about models of 530 billion parameters. So this is a huge change. And if we, those are different types of model. If we think on a specific architecture, on a specific type of model that we name it as transformers, we can see that the size has increased significantly in the last four years. Since they were released, we are getting bigger and bigger and bigger. So I think that the first thing that it is first to understand is why are we using bigger and bigger models? So that's a very interesting thing, because first of all, it has been empirically proven that the bigger the model is, the better it behaves, the better is the accuracy on the task that we want to perform. But also the faster it converges, which means it will reach to a good solution much faster than using a smaller model, which sounds kind of difficult to understand. If it is bigger, it will train in a longer time. So actually it gives the neural network to learn faster by having a bigger model. We will also see, and Marianne will explain that, how to make, once we have a neural network trained, how to make it smaller to fit our production perspective. So this is something that we are dealing with bigger models, very big models. The second thing is that thanks to a couple of advances, one is the attention mechanism and the transformer architecture, we were able to overcome some challenges that we have with previous approaches. I mean, with recurrent neural networks like long short-term memory networks, where the length of the sequence of the sentence that we wanted to operate with needed to be not that long. And that was because the way those neural networks were implemented would make the neural network to forget the beginning of the sentences. With the new attention mechanisms and with the transformer architecture here, we'll be able to train theoretically of any size length of neural network. For instance, in our model, we trained with a maximum sequence of 2048 tokens. Tokens are not characters, are not words either. We may say it's something in the middle. So with around 2048 tokens, you have a very long paragraph. But that was our own constraint because we decided to do that. And another very interesting thing that why we are seeing this revolution in natural language processing is the self-supervised learning. Basically, the techniques that we use to train these neural networks doesn't require the data sets to be labeled, at least to pre-train the language model. So that's incredible, because we don't need to label billions and billions of documents. We just need to use them, and we will use a few techniques like masking or whatever to learn from the existing text without labels. That's a very important thing. Okay, so we will do a two-step task. Let's say the first one is we will train a large-scale model, a language model, and we will see how to do that. And then we will just query it. That's important. We won't be doing fine-tuning, continuing training on a specific data set. We will query that data set, and we will learn how to do that, and Marianne will go deeper on those details. The technique to query the language model, the model we are training or pre-training, is known as future learning, prompt tuning, p-tuning, which is basically a very clever approach. By the way, let me step back for a second. We have a language model. What's that? Basically, it's a neural network where you add a few words, and it completes those few words until it considers it needs to be finished, because it says this is the end of the sentence, or because it reaches a maximum number of tokens that we pre-specify when using that neural network. So what are we doing? We are doing, for instance, a task which is translation from English to French, but we have not used a data set to train on pairs of English to French words. What we just do is, as input parameters, we use translate English to French. And when we add an English word, cheese, and we expect that the neural network completes the translation by itself, because a language model is what it does. It just completes sentences. So our sentence is this one, translate English to French, cheese, and prompt. This is zero shot because we are not adding previous examples. We can help a bit the neural network to say, okay, I want to translate English to French. This is a translation. Please complete this one. Hopefully, and excuse me, French speakers, this will produce fromage, whatever it is pronounced. Okay, so, but once again, this is a language model that the only thing that does is complete sentences. And by specifying the task and a few examples, we will make the neural networks to do things like answering questions, sentiment analysis, summarizing, and we will see that during the talk, okay? But the most important, the bigger the model is, the better it behaves. Okay, so this is 1.3, 13 billion, 175 billions. That's why we're seeing, because the performance maybe in a smaller model is not that good, but as soon as we make the model bigger enough, without training on a specific task, we will get very good results, state-of-the-art results. And this is basically an example that we created with our model. We have just a few examples of English and French sentences, okay? And we are expecting that it translates what rooms do you have available, and it will translate that. And the thing is that it just does it. Let me skip the video to save some time. Okay, so look at this. It just translates the sentence, and it continues generating other translation. Why? Because somehow it didn't understand that it needed to finish here. So a very important task on this kind of approaches is the answer engineering, which is basically pre-process the output to make it the way we expect it to do. So basically, once we find the end of a sentence, this is the translation in this task. But once again, Marianne will speak much more about this. So how do we do this? So basically, a 4 steps task. Let's load some data. Let's pre-train it. Let's query it as expected, and let's deploy that into production. How to download the data? So we use, by the way, you will see here in the slides at the bottom all the code we used, and everything is open source, the code and the data set that we use. So you can reproduce that yourself if you want to do that on your local language, because the aim here is that we don't only have local language models in English or Chinese, but in any language you can guess, we could try to do that. Okay, so we use a corpus, Oscar, that is a multilingual, and we decided to use the Spanish and the French part of that multilingual corpus, sets of documents. And we perform multiple tasks, and that we will see: text deduplication, language filtering, general cleaning, blacklisting. Here we have the links I mentioned before, where you can download the code that we use on each of the steps. So first, text deduplication. That's a very important task, because when you use a public dataset downloaded for internet, the chances are that there are lots of sentences that are repeated, because we repeat sentences. So why are we training a neural network with huge repeated examples? So the first thing that we need is to get rid of identical sentences or very close sentences also. So that is the text deduplication step, and here we have the script how to do that. Then we need to do language filtering, because sometimes if you use a forum or a blog, sometimes, and you want to capture Spanish text only, maybe there are English sentences. Why? Because a comment is written in English because the person is English, or in other language. So we need to somehow filter on our specific language. But there might happen other things. By the way, we use a neural network to do that, or pre-trained one. But we also did additional step, which is general cleaning, because maybe the data is corrupted. It can be corrupted. Or secondly, the text that you have is English, but it is JavaScript, for instance, or HTML. So we need somehow to clean it, and here are the scripts to how to clean it. We won't go into the Python details. And finally, we need to do a very interesting thing, which is blacklisting, is trying to make our models safe. Our exercise was to avoid the model to speak bad words, to swear, to have hate. So we use a couple of approaches. One of them was to remove any document, any sentence with at least 2 blacklisted terms. So basically, there are words that can have multiple meanings. Maybe one of the meanings is a safe one, a correct one, but the other is a bad one. So in order to do not remove any potential word that can have multiple meanings, we only remove documents with at least 2 different blacklisted terms, which is, it is increasing the chances that that sentence is not as good as possible. We could have used other approaches, but this actually worked really, really well. So in figures, basically, we had 2 data sets, one for French of 280 gigs, another for Spanish for 280 gigs also, and we deduplicated that, and basically it is the half of the data, which is good because we are focusing on the unique sentences and not on duplications of many of them. And after performing these steps, we got a data set of 120 gigs and 150 in Spanish. All this process only took 12 hours per data set. By the way, we didn't want it to be very ambitious on the hardware that we use for this exercise, and we took servers a couple of generations ago from our existing one for this specific task. If you are training bigger, the chances that you should go for the latest servers, but for this specific exercise, which is not that big, we just decided to use hardware that many customers we already have because it has been in production for at least 4 years. Okay, well, 12 hours each. We also perform a step, which is the tokenizing step, which is basically what you need to do is, as you know, computers do not deal very well with strings, but deal extremely well with numbers. So we tokenizing step is to convert our vocabulary to a set of embeddings or numeric representations, vectors of numbers that will be what the neural network will use. Okay, so that is the tokenizer steps to even, it does something additional, which is because words can be have multiple forms. I'm happy, happier. So it splits the words in a specific configuration that is very efficient to represent our corpus, and even unknown words also. So it works really well. So that is the tokenizing step, and it takes around 45 minutes, not that challenging. On a single node on CPU, this step is done on CPU, and it produces the vocabulary and the merges file. Okay, so that is what we did. This is the notebook of how to train it. And this is basically what is happening. Oops, sorry about that. You have here, you will see below that we have some sentence, bonjour, bienvenue à la conférence, and it splits the words somehow in a specific way, which is the interesting way for them. Let's say like that. It's a very simplified explanation. And we need one step else, which is now that we have our data set clean, without bad words, without duplications, we need to convert that to a binary format, to a map format. In this example, it took us 30 hours and 48 hours, which is a long time to convert a data set. We have good news because we have been working on improving these scripts, and now it can be done in a couple of hours, the more. So we have also improved this timing, but at the moment that we prepare this talk, this is what it took. Okay, so we converted the data set to a binary format because it is more efficient while training our language model. And that's all. That is what we did. And now we are ready to pre-train. But before pre-training, let's do some math. Okay, so basically, we are talking about a model of 1.7 billion parameters, and we will store the data in the model, the weights, in FP16. Okay, and also the gradients. And because we are using Adam optimizer, we will need to store 12 bytes per weight. So if we do the math, basically 1.7 billion parameters, 2 bytes per weight because we are using FP16, 2 bytes per gradient because we are using FP16, 12 bytes per optimizer state, which is what it requires Adam. It takes 25 gigs of memory. And that is only to load the model. But when you are, as you know, we have the forward and the backward steps in the training step. We calculate a lot of intermediate results between the layers. This is not counted here, but it can be much bigger, maybe 60 gigs. So it doesn't fit in a 16 gigs of memory GPU. So we need to think how to load that model on a server with multiple GPUs. So there are 2 techniques, basically. We can, because we are splitting the model on smaller chunks, we can split it in a vertical way. Okay, so basically we have a few layers in one GPU and a few layers in the other. Or we can do that, which is a bit more efficient, in a horizontal way. That is what we call tensor parallelism, which basically we cut the neural network. If this is the neural network, we cut it by half. And we by half or by a third or by a fourth, we cut it horizontally and put that part, that slice, into a GPU. And we do that because we can do that because the way matrix multiplication works, it allows you to do that. And it's much more efficient than the pipeline parallelism because of the hardware that we use, NVLink, and a few other things. So we decided to go this way. Actually, we decided because our nodes had 8 GPUs each. So we decided to split our model in 2 parts, in 2 GPUs. So this is a copy of our model that will be loaded in 2 GPUs. And we will have training 4 copies of our model in parallel. So we have 1 copy of our model, another copy of our model, another copy of our model, another copy of our model. So we will be using another concept, which is data parallelism, how the data will be split in use because the model is split into 2 parts. So 4 copies of the model, each of them split in 2 GPUs, tensor parallelism of 2, data parallelism of 4. And because we are not cutting in a vertical way, because it fits, we can mention that it has pipeline parallelism of 1, because it fits all, one of the lines fits in a single GPU. And that is our configuration. Let's say that we use multiple approaches from 2 to 16 nodes just to play with the different configuration that we have. And in case you're curious, here are the hyperparameters we use. We use a public source framework, which is NVIDIA Megatron LM. Okay, this is one of the 3 ways we have, or frameworks we have at NVIDIA to train large language model. I think Marianne will talk a bit more about them. And our target was to get a perplexity of at least 11. And that is what we decided to do. And I think Marianne will explain now how we did it, how we reached, if we reached to our target perplexity. I think that's all from my side. Well, and this is just an example showcasing that how it works. Basically, you have some input text, and you ask them to generate 50 tokens, 50 kind of words, and it will generate it. Here is the code to run that. And here is the sentence inference. By the way, does the text generation, the pure text generation works? So let's see. These are some examples in Spanish. So this is once upon a time, a turtle, and it completes the text like if it were a tale of a turtle. So the style, for those who are Spanish speakers, is really, it sounds like a tale. So somehow with the tip of once upon a time, it already learned that you wanted to generate a tale. But there are other things. For computing, quantum computing will take, and here you have some correct text that looks like technical text, or artificial intelligence will be, and it will complete it. So it looks like it does a very good job completing sentences, giving an input, a prompt. And that is the key thing, that once it knows how to complete sentences, we'll be able to use it to perform other tasks. This is exactly saying in French. You will excuse me, but I won't read this in French. It's better for all of us. But it's exactly saying a few examples of how to generate text in French. And I think that with all, Marianne will go and explain a bit in deeper details what we have just discussed. Thank you.
Thank you very much, Miguel. Hope you can hear me. I think there is a kind of lagging in your slides, so I see them. Hopefully, people are not experiencing the same thing. So I see them slightly different. So I still see the text generation with Mimi Spanish right now. So can you just try to share your screen again? Maybe just to make sure that we all of us see the same slides.
Just one sec. So hopefully you can see it now, the downstream task.
It's loading.
Okay.
Oh, all right. So I think we now are missing Miguel.
Sorry,
Oh, here
maybe
we go.
maybe you can share your own screen just in case.
Yes.
It's because it's something is not working here. Sorry.
Oh, okay. That is fine. So let me see if I can share my screen. Give me a second. Here we go. Screen share, share screen, and this one. So hope you can see my screen. Yes?
Yeah, we can see it.
Okay, good. All right. So thanks a lot, Miguel. So sorry for this little issue. So I can comment on the French model actually. So the model was not only generating, grammatically and semantically consistent text, but it was also able to contextualize actually the according to the input prompt that we were given. For instance, talking about how to say, talking about uh, uh, um, I think that we gave some examples about relativity, for example, theory, or some politics, and so on. Okay, so let me see if let me know if you see my screen moving, Miguel.
It works.
Yes.
It works. Yeah.
Okay, good. Right. Okay, so now let's focus on how we can make use of those large language models. And the first thing that we can do is to actually use fine tuning. So fine tuning those, so we are happy with the perplexity of those language models, and we would like to solve downstream tasks such as, let's say, question answering or sentiment analysis and so on. And one of the things that we can do is to to collect some labeled data. So let's say, for example, for sentiment analysis, collect some content and with its label, positive, negative, and so on, and actually either continue fine tuning the language model to solve this kind of problem. So as Miguel mentioned, so for the transformer architecture, so there are different families, but basically we talk a lot about encoder family or decoder family. So the encoder family is a bird, like a bird family. For example, a bird model is an encoder family. It has a special way of fine tuning where we add on top of the language model classifier, and we train actually this classifier in order to solve a classification task or question answering and so on. For decoder language model families such as GPT, for example, GPT-2, 3, and so on. So I'm basically fine tuning consists in training further to detect, to predict the next token on labeled example in this, for instance. So we take a GPT model and then we have annotated data with to do sentiment analysis and train the model in order to generate actually the sentiment label, positive, negative, and so on, by giving us input the document itself. But this can be very, very costly once we are talking about very large language models. And it's not very efficient to think about fine tuning this kind of models. There are other techniques. So Miguel mentioned already that large language models, they have special behavior, I would say, about on being very good zero or few shot learners. And actually, in this mode of zero or few shot learning, so basically to solve an NLP problem, so what we should do is to simply formulate the task and ask the model directly to generate the answer. And like as Miguel discussed about in zero shot mode, so we would just reformulate the task, such as translate English to French and give the prompt itself, like cheese, and ask the model to predict the next token, which would be hopefully fromage. In few shot mode, so we would give some examples for our model. Okay. However, we actually noticed, and we noticed also that on our French and Spanish language model, is the difficulty to find a way of describing the task itself. So let's have a look. So here in the table on the left, so you have some examples on how you would describe the task. Let's say, for example, for sentiment analysis, you would have a template here that you can see X, the movie is Y. So X would be the input, for instance, a document or like a sentence, a review. I love this movie, for example. And you add a prompt called like saying the movie is, and ask the model to actually predict why, which would be great, fantastic, and so on, that you can link to a sentiment in this case. So there are different type of templates that you can use. However, as I said, we experimented also that with our French and Spanish model, but there were a lot of studies that showed that those models are very, very sensitive to the way we are engineering the prompt. For instance, here you see on the right a table where you could see that, for instance, the model prediction, the accuracy of the model prediction was increased by, let's say, 10%. If I take the example of given a template which was X was created by Y to X is created by Y, for example. So by changing slightly the formula of the prompt, we could increase the accuracy of that model. So those models are very, very sensitive to the way we are designing this kind of a prompt. And actually, there is a recent area of research that is focusing on what we call prompt learning techniques. So let's have a look at prompt learning techniques. So it's actually suggests optimizing the task instead of optimizing the prompt itself, how you would like to change was to is and so on in the task description. So it suggests optimizing the task in a continuous space in this case. So prompt learning uses actually a prompt decoder that you can see here in red, which is an additional neural network. It's a tiny neural network that is going to be trained in order to generate a feature representation or for a task description. And this actually feature representation that we call prompt token are going to be trained in a supervised way. And in this case, actually for this prompt learning strategy, the language model itself, the large language model itself is frozen that you can see here in blue. And it is only used in order to optimize actually the second neural network, which is the red one, in order to generate the past representation for the prompt. So this kind of techniques are very, very promising because they showed very good results, and they are also very interesting in terms of deployment because the language model itself is frozen while you can actually optimize the prompt tokens for different type of tasks at the same time. So once you deploy your large language models, all you need to do in the same batch is to specify the type of task that you would like to show to solve. So in one batch, you can actually specify that you would like to do sentiment analysis, question answering, or document classification at the same time. And each of those samples would actually embed the prompt tokens that were designed, that were trained actually for this kind of task in this case, right? Okay, so if you are interested into this kind of techniques, actually in NVIDIA NeMo is open source toolkit. It is based on PyTorch, and we actually provide a tool implementation for prompt learning and p-tuning. So if you are interested into that, so I would encourage you to have a look at the tutorials that we are providing. Okay, so in order to do that, you will also need to actually convert your checkpoint, your language model checkpoint, into a NeMo format, first of all. And then from that, so this is what it showed on the bottom here, converting, in our case, that was Megatron LM checkpoint into NeMo. And then from that, you can actually collect the data with the format that is accepted by NeMo in order to prompt learn the task description for your task. Okay, so Now let's talk about deploying those models. So we train the language model, we fine tune it, or we prompt learn some task descriptions and so on. And we are happy with the accuracy of the model. Now, how to deploy those models into production, right? So before we go further, so let's have a look actually at the memory footprint of a model. Let's say, for example, GPT-3, which is 175 billion parameter model. If we take that model actually in FP16 mode, so the weights are represented in FP16 precision. So the memory footprint of this model is 326 gigabytes of memory. So I hope you can see actually the challenge at the deployment once we talk about very large language models here. So we need to we needed to develop libraries or techniques in order to optimize the deployment. First of all, by compressing the model, and there are different techniques for that, pruning, quantization, and so on. And then by distributing that model, even if it was compressed, in order to actually have an efficient deployment. So in the following, actually, we will be talking about some tools that we are developing at NVIDIA for such pipelines. So we talk about model optimization. So we take the model, we try to compress, to optimize that model by doing some layer fusion, quantization, and so on. And at NVIDIA, we have two tools that will allow you to do that, TensorRT and Faster Transformer. And we will see in the next slide the differences between Faster Transformer and TensorRT. Then we can use our Triton Inference server in order to deploy those models into production. And there are different features actually that Triton Inference server will allow you to use. And one of them is the capability of ensembling actually. And this ensembling mode is very important once we want to distribute actually the model into different GPUs, for instance. Okay, so let's have a look at comparing actually TensorRT and Faster Transformer for model optimization. There are some differences between those two libraries. So TensorRT will allow you to actually optimize any type of neural network, so not just related to transformer models, but it can also take convolutional neural networks, LSTM, and so on, while Faster Transformer is focusing on a very limited list of actually transformer models, such as T5, Swing Transformer, Vision Transformer, Longformer, BERT, Megatron, GPT-3, GPT-2, GPT-J, and so on. As I said, so Faster Transformer is going to be limited to a list of transform, but it is actually specialized for transformer layers. And basically, we would recommend to use Faster Transformer for for decoder-based models such as GPT-like models, right? Okay, so this is just to give you as a reference. So in our experience with Miguel, we're focusing on for the French and the Spanish model, we were focusing on Faster Transformer. But this is to give you an example on how you would do that with TensorRT, for example, if you would like to go for this solution. So first of all, what you need to do, so as I said, TensorRT doesn't support out of the box model distribution. So in this case, you will need to distribute by hand, I would say, like split the model and make a use of an ensembling of that model in order to deploy that model. So let's have a look at the pipeline deployment. So you end up with a PyTorch checkpoint. Let's say, for example, in our case, we trained our model with Megatron LM. So it's a PyTorch checkpoint. As we trained that with using TensorPalette 2, we end up with two chunks of PyTorch checkpoint. So the first thing that we need to do is to merge those two checkpoints in order to get one neural network. And after that, what we need to do is to actually use some libraries like Graph Surgeon, for example, in order to split sequentially this time the model. Let's say, for example, we have 12 layers, so we could actually sequentially split that. The 1 to 6 layers would be on the first chunk, and from 7 to 12 would be on the second chunk, for example, and optimize both those chunks of the PyTorch checkpoint using TensorRT and make use of the ensembling of Triton Inference Server in order to actually ensemble those two models, saying that the output of the first chunk is going to be the input of the second chunk in order to generate this. So this is how you would do that with TensorRT. In our case, for the French and the Spanish experiment, so we actually focused on faster transformer. So basically, faster transformer will allow you to deploy the model using pipeline or tensor parallel out of the box. So you don't really need to actually merge the checkpoint and then cut that sequentially and optimize each of them independently and build the pipeline. So in this case, with faster transformer, you can actually out of the box optimize that model using tensor parallel or pipeline parallel, or both of them if you want to. Okay, so the first thing that you need to do is to convert actually your checkpoint. So for instance, in our case, that was Megatron LM checkpoint, to convert it to faster transformer. And in this slide here on top left, you can see the script that we are using for that. So let's say we are targeting in our use case, we trained our model with tensor parallel equal to 2. So we are targeting distributing that model on 8 GPUs, for instance, here. And this script is going to generate the optimized version of that checkpoint. And by the way, so you can actually on here we have yeah, you can see my screen here. So here you have actually the link for replicating if you would like, and you can find the Python scripts here. And once this model is optimized, you can actually use the faster transformer backend of Triton Inference Server in order to deploy that model in a server. Okay, and faster transformer provide also a text generation tool that will allow you actually to experiment with your optimized model in order to see if there are a loss in terms of accuracy, for example, or not. And that's the idea. By using this kind of models is to keep the accuracy of the model while optimizing its memory footprint and optimizing actually the layers in this. And this is what we are going to see actually in the next. I will show you the inference with faster transformer using this kind of scripts that are available with faster transformer here. Okay, so here actually in this demo, so we are going to show faster transformer GPT demo in action. And in this case here, we are showing that for a model that is available that you can download. So this demo is available, so you can replicate that demo. It is basically taken a Megatron LM PyTorch model, an English language model, 345 million parameter model in this case. It's a tiny, I would say, model. And it is going to optimize it using faster transformer. So let's have a look at that. So hopefully I can play that. Here we go. So, oh, sorry. Here we go. So let me start here. So again, so I put the link here so that you can go and try to replicate. So first of all, what we need to do is to download the model. And this is giving you actually where you should download the model. And once you download it, you use the Megatron conversion checkpoint script in order to convert that model. And what we can do is to actually optimize the model with faster transformer using tensor parallel equal to 1. And then we can optimize that model also using tensor parallel equal to 4. In our case, in this demo, we used 1, 4, and 8. And each of them, you will end up with actually for each layer to have binaries according to the tensor parallel that we are showing. For instance, here for tensor parallel equal to 4, for per layer, we are going to have 4 different binaries. For 8 in this case, we are going to have 8 binaries per layer. Here you can see them, 8 binaries per layer. Okay, so here we go. And then after that, we can actually query the model, and you can see the cost of querying the model using the GPT sample Python script that you can have, and actually querying and specifying if you want to distribute that model or not. And you will see actually in this case, I'm not distributing that model. I'm using pipeline parallel to one, tensor parallel to one. You will see at some point that the GPU number 0 is working here for the inference, and we got 400 milliseconds. Now we are doing exactly the same in FP16. We reduce the latency here. Now let's distribute the training using, let's say, for instance, 8 GPUs. And you will see that all 8 GPUs are working in this case here to do that. Okay, so this is something that you can already try by your end. Okay, and we replicated actually exactly the same procedure with our optimized Spanish and French model. So let's have a look very quickly. We are distributing the model using tensor parallel to 2, and then we can we will see. So, for instance, the prompt that we were asking was la devise de la République française. And we are asking our model to generate one token. And hopefully, this token is going to be liberté, égalité, fraternité would be the next. And you can see actually the latency here of that model by distributing the model and so on using FP16 and so on. Okay. All right. Now I think it's time for conclusion. So yeah, okay. So let me put that. So in this journey, so we used publicly available data sets and code, and by doing that, we hope that we were able to demystify the development of large language models, so that anyone who wants to tackle that problem can get guidance, step-by-step guidance, or where to start actually, what kind of scripts they can start with in order to um, actually understand all the steps that are required in order to train large language models. And basically what we learn by doing that is, like, once we do it once, we know how to do it, and now we can focus on how to improve the language model, or how to solve downstream tasks, or how to improve the deployment of those models. We can customize the model, the hyperparameters. We can change the data set. We can actually improve the quality of the data set. And trust us, the quality of the data set is really, really important for large language models. We can also scale to larger model, and this is basically what we did. After training 1.7 billion, we scaled very easily with the same scripts to 5 billion parameter model. We scaled also the data set at the same time, and we actually obtained very, very promising results, good results actually, and surprisingly, the model converged faster in our case. Okay, so just I wanted to say a word about other languages. So in our experiments, so we focused on French and Spanish, because we are, like, I'm French speaker and Miguel is Spanish speaker, but there are like more than 6,000 languages in this world, and we need to actually to focus on those languages. Otherwise, so the millions of speakers will not benefit on what could actually add AI technologies in this scope. And there are some initiatives actually on multilingual models, such as there was a recently released a Bloom model from Big Science, or those machine translation models like the one from Facebook called No Language Left Behind. But I really believe that it is necessary to focus on local language models here. Okay, so and from NVIDIA perspective, so we are actively working in this scope. So we have the hardware and also the software solutions for training, for tuning, and also for deploying those models into production. And I would like to highlight a new tool called Nemo Megatron that will allow, this is a software that will allow you to train GPT and T5 language models efficiently. It will also allow you to do efficient data curation, and also it provides recipes for training different scales of those type of language models, and it will give you some tools in order to find the best hyperparameters at the deployment part. Okay, so Nemo Megatron is now open beta. If you are interested, so please just go to the Nemo Megatron website and apply. All right. So so we would like to highlight that we do provide also different type of learning, so workshops. So with our Deep Learning Institute, and we recently released a model parallel workshop focusing on how to build and to deploy very large language. Neural networks in general, and we will focus also on NLP in this case. And before we end up, so I just wanted to mention that if you want to see some examples of applications where large language models are used, I would encourage you to have a look at NVIDIA Project Tokyo and Toy Jensen demos. So they are available on YouTube. If you are interested, you can have a look at the demos. You will see examples of chatbot or avatars that are capable of answering different type of questions. And this avatar is powered by the 530 billion parameter language model. Okay. So with that, I think thank you very much, and we can maybe um, see if there are some questions.
Hello again, you two. Thank you so much for the interesting talk. For me, at least, it was very interesting to see some NVIDIA projects that are not necessarily tied to gaming. Was quite a few new things for me.
Okay.
Cool.
All right. So maybe you two want to share some insights with the audience and me on how you started programming and got into machine learning specifically.
Oh, would you like to start, Miguel?
Do you want to start? Okay. So no, it's just a joke. Well, I love my parents, and they had the great idea that at the age of 6, they decided to give me to gift me a computer. So I started at that age. How did I became a machine learning practitioner? So I studied computer science, and at any moment I was involved on working on financial services project in computer science, but financial services project. And I noticed the need that I wanted to switch to something that I really like it, which was artificial intelligence. So I studied at a very, had an age already, and I decided to just switch my career from financial services to AI, and that's what I did. Lots of training online, lots of studying, and that's all. Marianne, maybe you?
Yeah, in my side, I had a quite similar experience actually. So I started studying computer science in general, and from that, I was actually very interested in artificial intelligence. It was a long time ago, actually. That was not that much successful at that time, but I started to actually understand to have some algorithms, especially on in computer vision for recognizing patterns and comparing that with what we had at that time that were very successful by representing images with engineered features and comparing the results on what machine learning was adding by trying to extract automatically actually these kind of patterns of representing an image by using the data itself. And this is how that was the first time I started actually working on machine learning algorithms in general. And then like we started to talk about a neural network. At that time we were talking about, you know, perceptron, that was in French in my side. And then that was very, very, you know, simple neural network. And from 2012 actually we started to see like a huge jump in terms of performance by using larger data sets, different type of architectures with convolutional neural network and so on, that started really to give us a really very, very interesting results on computer vision first of all, and then we started to make use them of this kind of techniques for natural language processing. And it was actually something that we were expecting, actually, that this type of models would give us good results. We didn't know at that time how we would do that, but we knew that by taking data, a lot of data, we could actually train a way of representing this implicit rules of a language in our case. And this is what we started to succeed. And the first success actually started in maybe 2017, something like that. Oh, well, we had another success with Word2Vec, for example, which was a way of representing actually the language text in general, words, that was based on a neural network. At that time, it was in 2013. But the really huge jump is once we started to work on transformer models that were incorporating attention mechanism. And in this case, we really opened up a new generation of AI for natural language processing.
Sounds fascinating. Miguel, you told us that you got a computer at the age of 6. Do you still remember what kind of hardware it had?
Yes, definitely. Dragon 64. And since there are Amstrad CPC, PC 1512, 286, 386, 486, all of them. I mean, I've been around computers since I was really small one, but it was Dragon 64, the one I started playing with BASIC, basically.
But Miriam, do you also remember your first computer?
No, I don't really remember, to be honest. I remember it was a big screen. At that time, we had very, very big screen, and we could do really tiny things with it. But when I started programming, I started studying, first of all, algorithms. So algorithm is not related to any language, programming language. But first programming language that I started with was Pascal. I don't know, maybe people that are joining this session today, they don't know this language. No, but that's how I started doing that. And I do remember I had a project where we did a kind of a corrector, actually, of misspelling. So that was already on natural language processing area at that time. That was very, very hard to do in Pascal.
Can imagine. So we got a question in. What do you two think about the future of AI when data on the internet rise exponentially?
Well,
A very broad
I would
question.
say that if I may answer, I mean, there is neural network itself were invented, the concept of perceptron, as Marianne mentioned, in the 62 or something like that. So ages ago. But it was a lack of both hardware and data sets, but it did make them to do not success because neural networks usually perform well on a regime of data which is much higher than the one needed on classical machine learning methods like random forest of books. So now we are in a very great moment, which is we have the data, that increase of amount of public data with internet, and we have the hardware also provided by media. So we have both great combinations. We have a huge progress on hardware and a huge amount of data available. So and we have another thing, which is the unsupervised methods. So we don't need to label those huge amounts of data to use them. So with those three factors, the limits are on the movies. I mean, I think we can reach to anything we didn't expect to have 10 years ago, and we saw that the movies it's coming because we have, in my humble opinion, all the tools and all the pieces available right now. What do you think, Mariam?
Yeah, I totally agree. And I think the challenge today is to actually how to like make those models behave as we would like them to do, because like we can take the entire internet text data and we can train our language model, for instance, if we are talking about NLP, so to do different type of tasks and so on, so we can accumulate knowledge and so on. But now we are reaching another area where the most difficult thing is to actually, I would say, control somehow the behavior of those large neural network in order to get what we would like to have. So as we mentioned earlier, in our experiments, we made a lot of filtering of our data in order to make sure that the model is not going to generate inappropriate results, for example, text, for example. So that's the challenge where we are today. So anything related to like we can do a lot of things, and I think some of you, if you are from in NLP scope, so you heard about those recent models that are incorporated as a chatbot, where you can actually do conversation, and the results are quite actually impressive. So now, yeah, the challenge would be how to make sure that those models are behaving as we would like to.
Please, Marianne,
All right.
let me add an analogy that just 1 second. An analogy on what Marianne is saying, because it looks, I just thought about it. Imagine that you have a kid, and usually you have a couple of parents, and you teach it, and they have a couple of inputs. Now try to teach a kid that has millions and millions of parents with different opinions, with different knowledge. So that is what we are doing. We are taking millions and millions of behaviors and knowledge of people, trying to produce something that behaves as we would like to. So that's the challenge. I hope that makes sense.
Very good explanation again. All right. You two, thank you so much for the awesome talk, and congratulations on your really fascinating project. I wish you a nice rest of the day and see you soon. Bye.
Thank you for having us. Bye.
See ya. Bye-bye.
Bye. All right, and before we jump to the final speaker of the day, just a few seconds break. And now right back to machine learning with the final speaker of the day. He is head of data at CodeCentric. And when it comes to machine learning, he focuses on the necessary infrastructure and organization to help data projects succeed. Welcome, Matthias.
Hi. Hi, everybody.
Hi, Matthias. Thanks for joining. How are you?
Oh, good. Had a quite good lunch. Not too big, hopefully. So I'm not going to fall asleep likely. Maybe you do, but I try to wake you up.
Under no condition I will. So, Matthias, would you mind telling us just real quick about what we are going to learn from you today?
Yeah, so it's, as you said, I'm focusing on infrastructure and organization. So I will talk about how to actually get your model in production. Okay, this sounds quite lame, but what challenges do you have and what did we do on them? So also like the engineering and science gap, the automation part of it, doing this in the cloud and not throwing a lot of people on it. I think this is pretty much the summary of the talk.
All right, Matthias, you got my full attention. And without further ado, the stage is all yours.
Okay, thank you. So continuous integration for machine learning. So this is the story of a project we actually did. And pretty at the beginning of the project, we thought about, okay, we need to get better. Why did we need to get better? What was the initial situation we were looking at? So in general, what were we doing on the business side? We were doing demand forecasting based on transactions and other data. I think this is this is more than enough to actually understand what challenges we had. We had some other challenges on the data and the machine learning and the data science as well, but this is not part of this talk. So this was a startup. So, and everything was done in notebooks. In this case, there were Databricks notebook, but I don't think that matters too much for the general setting we have here. So, and in the notebooks, there wasn't just doing experiments on the data, but really like everything was in notebook. The data preparation in ETL, loading data, preparing data, getting data from some sources, and so on, was done in notebooks. Training of models, it's actually regular training of models, not one-off models, were done in notebooks. Predictions based on these models, we were mostly doing batch prediction, not too much online predictions, were done in notebooks. Validation of the results as soon as we got the feedback were done in notebooks. So really all the bad parts of notebook. I wouldn't argue that you can only write bad code in notebooks. I think you can write really good code in notebooks as well, but this was really only the bad parts. Displays, prints, plots, and on the right you see some of the directory structure. Notebooks actually were named, they weren't untitled. And then you see like 1, 2, 3, which order to execute them, and here were 2 twos, not sure which notebook to execute first. So we had quite some notebook legacy. And the situation was like we had the business, in our case, those were external clients. They get they defined the scope, wherefore should we do demand forecasting, for what articles, for what groups, and so on, and for in which what are the parameters we should include in the demand forecasting. And they were doing the validation on the demand forecast we made. So they gave us feedback. Was it good? Was it bad? Mostly in the form of, okay, we sold this much or we didn't sold this much. So this was quite a good feedback. Then we have the data scientists and engineers, and we can discuss if it's really a good thing that scientists directly discuss things with an external business without any filter between this, but also out of the scope. They were doing the data preparation, they were doing the training, ad hoc trainings, trying to find the best model, doing some based on the validation, trying to improve the model. And in the end, we had some cron jobs, or at least some jobs that were running in an automated fashion at specific time intervals. This was basically the data import. So the external client gave us this data, the transaction data, and what else. Or we imported it, did some preparation on this, did the training and the prediction. And you see here already we have training both manually done by the scientist and automatically by the cron job. And this was already one of the problems we had. So 2 main problems stand out. First of all, we didn't have a development and a production environment really. So people were working on new models, but this directly inflicted the training of the model. So even when you're doing experiments and so on, in the night there might be the regular automated run, and it would just take your latest development code. So this actually, who would guess, to weekly failures of prod runs, the prediction changed and nobody noticing. And in the end, people didn't really dare to work on anything because they always thought, okay, I might break production. And we also didn't have a chance to really put a distinction between training and prediction. So every time we wanted to make a prediction, we actually retrained the model and did a prediction. There was no chance for us to do prediction with other data without retraining the model. And the experiments also overrode the production predictions in this case, because we didn't have this we didn't have dev and prod separated, we didn't have models and predictions separated. So as soon as someone was trying something in dev, he actually ended up overwriting predictions in prod. And now some of you might say, seriously? I mean, this is what you just tell me is just basic stuff. I mean, from a software engineering perspective, and my background is definitely software engineering, you would just think like, okay, how could this company ever becoming alive at all? And therefore, a few words on the circumstances why this it still doesn't make sense, but there is an explanation for this. So this was a startup from university context. The first focus was getting a good model for a demand forecast. What they were doing was basically individual software development for their client. So the client gave them the data, and they did the training, they did the data preparation, and they also had some small application bit on this. This was quite reused between clients, but the data part was a lot of client-specific stuff. But the business impact was actually proven. So the clients were quite happy with this because the prediction were so good, it was better what they had before. So yeah, business impact, and we had more clients that were coming up and wanted to use this solution. So there was until then, mostly manual work, ad hoc work, but in order to scale, we had to automate a lot of stuff. So it was quite in the early days of the startup. And a startup not built by engineers, but a startup built by data experts and business matter experts or subject matter experts. So what was the first approach we would take when we designed a new solution? So this was the really first sketch, and getting already there was a good thing for us because it actually improved stuff. So the one thing is, okay, we had the data extraction and preparation. This was one thing, but the data preparation, training the model, and evaluation, this was basically work that the data scientists did. And the data scientists were like half of the engineering department. So a lot of data scientists. They focused on the data preparation, model training, evaluation. And the output of this should become a model. And we put this model into a model registry. Doesn't sound too fancy for now because, I mean, model registry by now is quite common. I will come later to how we extended this and what tools we are using. So, and after this, we had this model registry, which was a cutoff point then. So this was the first point where we actually cut training the model and doing the prediction. So really say, okay, training the model is completely independent from doing the prediction. We could train a model and register this in the model registry without changing the prediction service in the end. Prediction service sounds here like more like an RP or something like this. It was just another batch job that was running, getting the model and doing demand forecasting on a really big bunch of data, not on an online kind of fashion. So we had the separation here between ML, the ML part, and the ops part operating this stuff. And we also had the separation between dev and prod, at least in a bit of scale. We were still using Databricks notebooks, and we used MLflow. I mean, this is super good integrated with Databricks, and I think also MLflow without the Databricks stuff is still a really good tool and really helpful to use as a model registry. So we just sticked what we had in hand and was quite okay for doing this work. But what we still were stuck at data extraction, data preparation, model training, evaluation, and validation was still in notebooks. So we didn't get rid of this in the first place. What we then started with, this was at the time when Databricks released the repository feature. By now, I think it's quite sophisticated already. We moved stuff, so the notebooks, into the repositories. What Databricks repositories offer you, you can basically just say, hey, this is my data, this is my Git repository. Please store my notebooks in there, and you get the basic things that Git has. You have Git, you have commits, okay, but you also have like branches. You can do push, a pull request, and something like this. So, and we use this to actually distinguish between production and development. So we had the main branch, which was always like the production branch, and we had development branches where everybody could test new things and so on. And as soon as it was ready for production, we just did a merge request to the main branch. Pretty self-explanatory. So this was also one thing to help us, okay, give the people the confidence to work and change and do experiments and be sure we are not going to break production. And then people started again to say, okay, I can actually try things. Now the challenge, it's good to do this on code. The other thing is, if you're working with data, you also need to separate the production data. Therefore, we just namespace the databases. As soon as you're using another branch than the main branch, it would automatically detect this in the code, because in Databricks, you know which repository, which branch you're in, and just used another data store for this, for writing data. So summarized, so until now we had training and prediction separated. We had scripts and notebooks which were at least source controlled, so we could do merge request, pull request, and code reviews, and that produced models, metrics, and visualizations for this. But it was still manual stuff, script-driven, interactive. There was still a lot of people just skipping through notebooks and say, no, I need to change this, then I print something here. There was still not really an automation behind of it. There's still experimental code written and executed in notebooks to find a model. And we still struggled to get from this experimental code to production code, to automated, to really engineered good code that is reliable. So, and we still had the disconnection between ML science, who worked in notebooks, and the engineers and operations. Yeah, there was something like this model registry where you can just, hey, this is the model, use this now. But still was kind of tricky. And we didn't have anything like continuous integration, so no tests at all. Both code nor data was tested in this case. And deployment, okay, we published a model to the registry. This was basically the only deployment process we had until here. So until here, we just had deployed the trained model as a prediction service. I think you can, if you look around at the internet, read it to data science or some Medium tickets, you find plenty of examples which just tell you how to get a model. If it's pickled, if it's in TensorFlow model, if it's an Onyx one-time, whatever, to get it to a service where you can put requests again. This is not really hard. This was good that we done it, and I think it's really good to aim for this as an absolute minimum. And it might even be completely sufficient. You might not need all the things that coming next with all the automation and retraining and all this stuff. It might be completely fine. Working on a model, deploying this as a prediction service, if the model rarely changed, and if the stakes are low. So even if the model needs to be changed, it might take a day, 2 days, a week. I don't care, because on the other side, the consumption of the model is maybe even someone there who is, there's a man in the middle that sees, okay, or a human in the middle, or a human in the loop, that sees, okay, the model results are garbage. I know what to do because I can handle this myself. If it's a completely technical automated process behind, which is directly connected to financial stuff, for instance, or ethical or morality stuff that is decided, you might want to be better here. So now you're going to ask, okay, so you not taught us the basics. What's next? What were we missing? What we needed? We actually wanted to really continuous experiment with new model implementation. Therefore, not only fine-tuning an existing models, but really trying different models. At first, we were just using GLMs, but we wanted to try, okay, can we get better using neural networks or other fancy stuff? We wanted to do a frequent retraining with the most recent data, not only every 3 months, but basically every week, and see if the model gets better or not. And we want to improve reuse and composing of existing artifacts. By now, we were mostly like doing, okay, we have this done for customer X. We just copy it and change it a little bit and doing things different for the next customer. But basically, we just had another implementation of it instead of, okay, we have the same implementation, just change some config and run it again, and we are done. So really was really important to scale it here. So the next step was like, okay, let's have a look at the pipeline we are doing. You might recognize data extraction and the green box in the middle. This is basically the same as before. We do data extraction from our database, do the preparation, training, and evaluation. But the output of this is not a model. The output of this is basically the Python code that does the data preparation, that does the model training, and that does the evaluation. So not the model itself, but just the code in the end leading to the model is the result of what the data scientist did. The data scientist didn't say, hey, here is the model, you can use it, but they said, here's some code that prepares the data, trains the model. You can run it somewhere. And yeah, so I mean, code belongs in a code repository, so Git. And after this, we just ran a CI pipeline. We tested that code. We actually wrote unit tests for these experiment and orchestrated experiments. I mean, this is nothing else like, okay, take the data, do some preparation on it, train a model, and print out some metrics for evaluation and validation. It's an experiment. And this was run in a CI pipeline. There were done tests on it, both on the data part, both on the code part. And if it all was successful, the result was a Python package. And in the next step, the Python package was used for actually doing the training. You see it in the upper right corner. We're starting in the upper right corner in the packages. There was the CD pipeline for training. So at specific times, or if someone says, okay, this is a good package, I want to test it, this was deployed to the training environment. And then the training could be triggered. I come later to what might trigger a training. And the exact same code that was written by the data scientist is now executed to actually do this training. And the result of the training was a model, and then we're coming back to this one. And in the end, we also had a CD pipeline, so a deployment pipeline for the prediction service. So not every model that was put in the model registry was automatically pushed to the prediction service, but there was also like some quality gates, testings, and so on. Does the model converge? So to deploy to the prediction service. And we also had a rollback mechanism to say, okay, this model isn't good enough or behaves worse than expected and worse than the one before. So let's roll back to the one before. So yeah, we did deployment of a training pipeline, the continuous training and production using fresh data. We modularized the code. So this pipeline, this green box was actually a modularized code that could just be configured. Take another hyperparameters, take this as a data source, use this 2-3 business-specific words, and they were handled within this green box. And it was reusable across customers then. Yeah, they were usable, composable, and we did the continuous delivery of models to the prediction service. So, but we need an abstraction for this. So we are sure, okay, it can't be notebooks anymore, because notebooks were, in our case, quite coupled to the runtime. So notebooks could only be run on Databricks, in a Databricks notebook format. They couldn't be run anything else. We were still using PySpark underneath, but we want to get rid of this Databricks connection. We want to run it locally for developing, for instance. We want to have a reproducible, so some kind of container, some kind of format that can be run and so on development, which might be local, on production, and development might also be on Databricks. Yeah. And for isolation, this. I mean, some people will think like, okay, you're talking about environment, runtime decryption, so okay, we use Docker. Okay, in this case, we were just using Python packages. I wouldn't say that Docker wasn't possible as well, but Python packages for us was just one abstraction level higher, and we don't have to care about the environment a lot, but only on the code here. So yeah, we were building Python packages from an engineering perspective. Nothing fancy. We try to keep it simple. We were using Poetry for packaging dependencies. In my opinion, one of the first project which actually has a sane way of doing Python packaging and dependency management. We were using Cookie Cutter to actually have a template for those projects that look the same, that has the basic stuff in there, so that the data scientists don't have to care about, okay, I have to set up a Python package now. What do I think about? It was just Cookie Cutter answering 2-3 questions, and was everything generated. Test with PyTests, okay. And 2 things maybe. The one thing, we still had a chance to use Databricks Connect, which gives us the chance to connect to Databricks from a local IDE and still accessing the data, for instance, in Databricks. Disclaimer, I think Databricks Connect is by now, or since a few weeks, not supported, or at least not further developed anymore. They have a solution called DBX, which also includes not only connecting to Databricks, but also the stuff of packaging this stuff, deploying this to Databricks. So a few things we were talking about here, they try to handle it with this library. And we still had the notebooks in the repository. So this repository, the demand forecast repository, had in the demand underscore forecast all the code that was belonging to the Python package, really like a plain, simple Python package. And in the notebooks, it still had Databricks notebooks. Good thing on Databricks notebooks are not represented as JSON like Jupyter notebooks, but they are represented actually as Py files that can just be executed. And this repository can then still be used in Databricks. So one could still work on the notebooks, and if you're checking this out in the repository, this repository out in the IDE, you still have access to the notebooks and can see, okay, what did people do in the notebooks, and maybe transfer this to your Python model. And by now, the repository feature in Databricks is as good. You can also open non-notebooks file in the Databricks UI, so you can actually work on the demand forecast Python package from Databricks. So how does it look now? So if someone is changing the training code, it's committing it to the Git, to the version control. In our case, it was Bitbucket. We were building and published the library, in this case, to Nexus. And on Databricks side, it was getting the Python package, running this training code, and this training code created an experiment in MLflow. So we tracked every one as an experiment. And if the model was good enough, it was also publishing the model in the registry, and the model then had the link to the experiment. I mean, this is just basic MLflow feature. And from the registry, we could then use this either as a Spark UDF for batch processing. This was what we were using most of the time, or you can use the MLflow model serving features to actually get a REST API on this. But there was still this thing between experiment and production grade code. So in experiments, you were just writing in notebooks. You can just do notebooks still, and with the MLflow integration that was in the training, we still got the tracking of these experiments. And on a production grade code, you still have, as mentioned before, in the training, they were done the tracking of the experiment. So even every productive one was just tracked as an experiment, but as a difference to an experiment, there was also done the model put into a registry. Experiment, just creating an experiment, production one, doing experiment, and putting in the registry. But you see the dashed red line between the notebooks and the script on there. And this is still something where I don't have the answer. I have some possible answers, but this part of, okay, how to get from experiment code to production code is still a tricky thing at some point. Yes, you can use notebooks, and you can use notebooks to write production code. Other people would say, okay, why use notebooks at all? Directly start in an IDE and write Python package code. Don't even go to notebooks. I mean, those are the extremes on the spectrum. I think the truth that work, and the truth might be in between, why the extremes might work for people as well. I talked to people, I discussed this with them, they really said like, notebooks? No. Why notebooks? We always work in the IDE and working on Python packages. Then you likely are in an engineering heavy surroundings where a lot of engineers are available and people maybe also doing the data science stuff coming from an engineering background. And I also had settings where I say, okay, Python working in an IDE, building packages, I never learned this. So the other extreme is totally valid as well. So yeah, and for us, this thing was still coming back later. Maybe a few things in the training that stand out. So we mentioned which package was used, which Git commit. By now, we also reference the training data, which was used, the exact date of the state and training data. This is made possible by the data lake feature of Databricks. Yeah, and quality gates, we have them, but we don't have them separate. It's just part of the training code, the validation there. How do we manage all these moving parts? Data preparation, you see here, data imports, create a common schema, which is also data preparation, then do the forecast, which should only be done on certain days, verify those predictions and export them to the customer. This was all orchestrated by Airflow, in this case, and managed Airflow by Astronoma. But this was really only the orchestration, no data processing in Airflow. And data processing was only done in Databricks, and we had this managed service for less than $180 a month, and we had like 30 or 40 flows in there, like 2 to 3 flows per customer, roughly. Everything was configured as infrastructure as code, both the jobs in Databricks that were actually doing the training. Here you see, okay, the reference to the demand forecast py package, the parameters that were passed to this py package, so which method and which module to run in this package, which Spark cluster to use here, and in the Airflow pipeline, you have here like a Databricks task, and this is the ID of the job in Databricks, so that Airflow can run this Databricks job. So CI/CD for ML was, for us, basically the development. Output of the development was the source code, the pipeline then for building the source code to a package, then deploying this package so that we get an automated training pipeline, then coming data to this automated dating pipeline. We're doing a continuous training on certain intervals. For instance, new data. Every week, whenever we detect a shift in data, data drift, when we see a shift in model quality, there might be various triggers, and then the model moved to the prediction service using a continuous deployment thing. This was pretty exactly this what Google also suggests here. There's the link down there as an MLOps for framework and pipeline. So really recommended read this web page. To sum up, this is continuous integration for the training code. There was one CI part, test like feature engineering logic, does a training converge, some edge cases that was done there. And we have the continuous delivery at 2 times. Once we deliver the Python package to the automated pipeline, and we deliver the model to the prediction service. Yeah. And also having tests in there, verifying prediction performance for the model, for instance, doing some load testing as well. Yeah. And for the pipeline deployment, there wasn't only a production environment, there was also a pre-production environment where we actually could test the pipeline with real-world data before moving on to the production pipeline. So ML in production can be more than just an API. So all these automated stuff, the ML pipeline that can do the retraining, do the deployment of the model, and do all this automatically. It could be more than this, than API. It must not be. So be careful at which point you are standing and what is sufficient for your use cases. What is the business requirements you have? Do you really need this all in? In this case, it was a company that was that their sole service was this prediction. I would say this was needed, but there might be cases where the prediction service is enough. So now we talked about solution, a few words on challenges. And I already mentioned this one, the engineering know-how. Currently, when we're doing the writing Python models, we basically do a rewrite of the notebook stuff. The way repos feature make this easier, yes, but it could still be better. And at least in our situation, we had some cultural mismatch, and really from both sides. Software engineers, when they just were hearing data, they was like, oh God, Databricks, this is the black hole. I don't know what they're doing there, but it's not engineering. I don't want to have anything. This is kind of black magic. Leave me alone. And on the other side, also data science that say, okay, Git, IDEs, okay, Docker, Kubernetes, no way. So a few times quite a clash on this. And this was really like a lot of communication, a lot of building understanding and trust to actually get these people to work together. So as an ops software engineer, one tends also to over-engineer. I would say aim for low friction solutions. A data scientist isn't an expert in Kubernetes. You can't expect a data scientist to just say, okay, hey, just spin up a service in Kubernetes here, write your YAML file and the deployment and load balancer, and here you can have a sidecar as well. They would just say, hey, what do you want from me? So clean, easy solutions that provide a golden path for the scientist to do his work, that supports his work, and a path that the scientist actually wants to use. He doesn't want to use anything else. He just wants to work with this because this is the best way. He doesn't even think about other solutions. And this most of the time also means don't use every shiny tool on the market and throw it at your platform and at your data scientist, because there might not be a real value and they might even lead to confusion. And as a data scientist, I would have the wish of, okay, running things stable in production has some other requirements, some other needs than doing experiments. And it's okay that you're not, the data scientists are not the ones that build this production system, but they have to keep it in mind, okay, it works, it's not in production, that there are differences, and they might even help to close this gap so that an engineer is really easily able to move this step into production. One thing, cloud platforms. So this cloud platform I designed, this solution I speak about was basically Airflow, Databricks. Yeah, we had some Bitbucket, which was SaaS, and we had Nexus, which was SaaS. About 30 users, engineers, and scientists working on this, and it took about a capacity of 1 to 1.5 full-time employees for administration, for enablement, documentation, further development of stuff, and some kind of governance. So at least having keep governance, I mean, with both access rights, but also the part of, okay, who can use how many resources, how many users are used at all, keep the costs in some realistic and good scenarios, because in Databricks, you basically can burn a lot of money if you're not careful enough. So, but this means people were unable to do this themselves. It was clear for them, okay, if I want to do this and this, I have to do those 3 steps, and they could easily do this. We provided Spark, we provided Airflow, but everything else is self-service. If they just needed a new repository, they could easily do it. If they just needed a new pipeline or data store, they could easily do it based on the things we provided them. So just creating a new Airflow pipeline was a matter of 30 minutes max. Creating a new repository, I mean, cookie cutter update, that's it. A cookie cutter and add it to Git. Creating a new Databricks job and configuring this and getting it up and running in an Airflow, 30 minutes at all. So this was really from an engineering, from an info perspective, really thin and really, really easy to use. About costs, yeah, ranging from low to high 4-digit. It was consumption-based. We had better amounts, we had worse months, but the overall tendency is, besides having more workload, more customers on the platform, the cost would stay constant, maybe even going down a bit. So, and therefore really create some governance, cost, naming things, doing some structure, enforcing this structure also in Git repositories by cookie cutter, in when naming jobs, for instance, in Databricks, having some structure there really helps to get your way around if you scale your processes or machine learning processes. And now one of you said, okay, that must not be cloud. It could easily be Kubernetes. And I would say, yeah, no. Not a strict no, but if you want to build this on Kubernetes using Kubeflow or the open data pack from OpenShift or so on, yes, you can do this, but be sure you know Kubernetes, users know how to use Kubernetes, or the users don't have to touch Kubernetes at all. In my opinion, Kubernetes doesn't add any value to your product. You're not paid for running a great Kubernetes most of the time. So if you want to use Kubernetes, make sure that the users really don't have to touch Kubernetes, especially not data scientists, but also data engineers. Their job is not to work perfectly with Kubernetes. And my opinion, therefore, using DAF offerings is most of the time a better way to work on this than using Kubernetes. And yeah, if you're using Kubernetes, don't build it low level. Use some of the high level offerings, Kubeflow, Salton, something more, whatever is available there. So yeah, sum up, 40 minutes over. Developing an ML model fast is great, but it comes with long-term cost. You have to think about how to automate this, how to get this in production at some point, and maybe even how to scale this. ML in production, MLOps, I mean, this is bullshit bingo buzzwords right now. You hear them all the time, and it's just not deploying this stuff. It's also pipelining, automating this stuff, and it's the monitoring part. And I didn't even talk about monitoring here. I mean, there's things like Anomaly AI, where you put together data, put this in some whatever store you want to use. You can use Grafana and Prometheus. There might be some all-in included solutions. You can use functions that are included in weights and biases and so on. So, but monitoring is even a part as well. Then look at your requirements. Don't use every shiny tool that is out there. I mean, for all of the tools I mentioned today, I think there are 3 to 4 to 5 to 10 alternatives all the time. Might be feasible, might not be feasible. Have a good look. Also, what skills are needed to run this, and what is the maturity of those platforms. Cloud platforms, in my opinion, really are mature and help you with this. And an engineering know-how and mindset is helpful if you're working on scaling and automating this stuff, and if you're doing the ops stuff. Okay, that's it from my side. This was actually the last slide, so I'm happy to take questions.
Matthias, hello again. Thanks for the awesome talk, and kudos for not falling asleep after you had lunch.
Thank you.
I'm seeing
talked.
Sorry, quick problem with the camera. Oh no. All right, maybe just we'll continue with just the audio. No?
Now you even have lost the audio.
Okay, audio is back, and I think we just switch to. Okay, it's not working. Okay, I will have to join the studio again. Please, 1 second.
So I would play some waiting music, but I don't have it at hand right now.
It's one of the best events, or if not the best event.
All right, sorry for the interruption.
No problem
we have
at all.
finished with the webcam. All right, Matthias, so maybe you want to share also with us how you came into contact with software programming and maybe with machine learning in particular.
So software programming wasn't to get in contact. I mean, I started working as a software engineer, so I'm really having a software engineering background. And I was, when I started Concentric, my then boss said, "Hey, Matthias, you might want to take a look in Spark and Cassandra." So this is how I get into the data tag, and then it evolved into, at some points, data was also like this ML stuff. But I always say I can call a train method, I can call a fit method, and I call a predict method. If the data I put in makes any sense, I don't know. A little bit on the point, yeah. But I'm definitely on the engineering side.
All right. You also gave us some sources and material during your talk, but maybe do you have any more like blogs, books, YouTube channels, courses that you can recommend to the audience?
No YouTube, unfortunately, because I'm not the audio video type of learning. I'm more like the reading type. So yeah, I already mentioned the Google Cloud stuff on MLOps. Also, the Martin Fowler has something on this blog on CI/CD for ML, also really good stuff. And if you're looking more into the general data engineering, data tech stuff, there's some, by now I would say it's quite a standard. There's Designing Data-Intensive Applications by Martin Kleppmann. Really a good book. Absolutely, it's not totally basic, but it really sets you the foundation on how to think about things. And after this, reading this, I think you could be much better in getting, okay, this tool is aiming at this one, this tool is aiming at this one. This really helps to navigate the tool landscape in the end as well.
All right, thank you. You are head of data at Codecentric. Maybe you can give us some insight on like a normal work day at your workplace, if there is something like a normal work day that is.
For me or for a usual Concentric employee? So in my role, the head of role is more like, okay, I'm also doing a lot of expert consultings. I'm doing some also project consultings for long-term stuff. This was what I was talking about. I'm doing stuff on what topic should we focus on as Codecentric from a data perspective. This is more like, so mine is really like one day isn't the same as the other. But we also have a lot of really, really good consultants in the data area, and they're most likely like 4 days a week in a project with customers, helping the customers building their solution and also enabling the customers to build them and expand their solutions themselves. Yeah.
All right, Matthias, thank you for sharing so much insights today with us. I wish you a nice rest of the day and hope to see you soon. Bye.
See you soon. Bye-bye.
Bye-bye. All right, and sadly, we had to cancel the last talk of the day last minute, but we are in contact with Gada and she will record her talk and we will provide it on our watch section as soon as possible. And now that this live day also comes to an end, we want to thank our community partners of the day, namely Linz AI, Vienna Deep Learning Meetup, and our friend Patrick Lober. Also, now after this last live day, go to wordcongress.dev to get further information on our World Congress, which will take place in summer 2023 as an in-person event in Berlin. And as the year is also coming to an end, this was the last live day for 2022, but we will return on January 18th, 2023 with one of the true classics, Java. If you are interested in maybe having a talk on yourself or giving a talk on yourself, our CFP is open. Please apply with just the link under me. And now, thank you all so much for joining us today. I wish you a nice holiday season and see you next year. Bye.